Can you? I think she sees, right? I think she's working something else. Yes. Yeah, sure. Okay. Yeah, good. Yeah. So first, let's look at the prerequisites. I don't know, like in the Moodle page, I put this already, but if someone has forgot to do this, you can just download these things while we are doing the introduction. So it's there, the links also, and the slides also there in the Moodle, so you can download basically, and then see the prerequisite site, and then download these things. After the installation, we can do it together basically, creating the environment and everything, so we can do it together. So you don't have to worry about that. Just download this and install, because it takes some time to download and install basically. That's why I put it in the Moodle also beforehand. Rest doesn't take much time to do it basically. So we can do it together when we are actually there on the hands-on sessions. So let's look at the introduction first then. So first of all, I would like to say, give me a second, it's it. Yeah, recording, yeah. So, what is Kratos Multiphysics? Okay, as name suggests, okay, it can be something related to multiphysics, but beyond that, it's basically a source code plus a community. Because it's a community-driven open source multiphysics framework. So what we value is basically, as well as a source code, the community as well, to grow together basically. That's basically the spirit of Kratos. So everyone works together. So now, this is some highlights of the community, not everyone, because it's now more than 100 developers who are contributing like in different continents, even from Australia, from Spain, like in different places and different universities. Basically, more than 100 developers, active developers are there, even though the GitHub says it's around 180, but active developers are around 100 or 120 or something. Yeah, and it is being contributed by different companies like Altea, Deltares, and different universities, but not all of them are mentioned here because it's too much to put everything in there. Yeah. Now we'll be just showing some nice pictures and nice animations just to see that what Kratos can do. That's because this is just introduction. Yeah. First thing is we want to try for efficiency. That term stands for computational efficiency. So you can see there are a few simulations you can see in here. One is the PFM implementation in Kratos in the left. So you need to have really good efficient solvers to actually simulate this kind of behavior, like rock falling into a fluid basically. And in the right, you see the MPI parallel tunneling process basically. So we are basically Kratos multiphysics in the backend can be MPI parallel. What do I mean by that? It's distributed memory. A small question. How many of you know when I say distributed memory and shared memory? Okay. So, let's start with the shared memory then, small introduction. So for the shared memory parallelism, what do you mean by that? If you take a look at your laptops, they have more than one core most probably. And then, but they have one RAM, maybe 16 GBs, I don't know. Not sure. I think the byte, German words, I'm not 100% sure, so I'm not gonna talk about German words. So, yeah. So this same laptop sharing one RAM, like 16 GB in multiple cores, is called shared memory parallelism. So the each core is sharing the memory in one computer. Think of, I don't know, you know about LRZ in the tomb. So it has 100, maybe 1,000 computers connected to each other by something called InfiniBand. It's something like network cable, but it's a bit advanced. So then you can run your same program in those 1,000 computers at the same time, distributing the workload. But in that case, it's called distributed memory because every computer will have its own RAM and it's distributed among all these 1,000 computers. And then your one program runs it. So that's why it's called distributed memory. We call it sometimes MPI, parallel also. So I might use these two words like in alternatingly because sometimes my mind comes with MPA, sometimes I call it distributed. So just bear with me with that. I will try to be consistent, but I might not be because those two words are the same for me. Yeah. So that's it about shared memory parallelism and distributed memory parallelism. We won't be talking about those advanced topics today because that's, I think I need more than 2 days actually for to cover all of these aspects. But this is just a, I would say, basic onboarding which we will be doing today. But if you have any advanced questions, I'm fully open. When we go through, you can just ask, no problems at all. So this is about the efficiency. The next thing is, since it's called multiphysics, we need to have multiphysics. So you can see in the top, the left one, so you see a wind turbine, actual wind turbine, which has a fluid structure interaction. That means wind passes through it and the tip changes, tip moves, basically. And then how do you simulate this kind of interaction? And this is not purely done with Kratos, it's Kratos plus, as far as I know, open form or tau, maybe mix of them. Yeah. And in the top right, you see one of the benchmarks, you see how the mesh changes. To do fluid structure integration in this kind, you need to have a really good measure because your mesh changes a lot, because your deformation changes a lot. This is one of the benchmarks. It's fully done by Kratos. So the measure and the fluid and the solid part is in Kratos. So Kratos doesn't not only allow coupling in between Kratos, but it allows coupling with the external tools also. Basically, we have interface for that also. We are working on extending it to further applications also, like star system plus and everything. Basically, we are working on it to get the benefit of everything. Yeah. Next comes the particle methods, because Kratos does not only allow FEM-based solvers, but it also allows particle methods. So you can see in the top left, yeah, in DEM, discrete element method, so you have this kind of multi-spheres, and then you have this backhoe kind of action, and then you have the material point method application in here. If you are interested in these kind of particle methods, you can take part in the course which is organized by Veronica Singer, a colleague of us. It's, I don't know the date, I think it's happening on Mondays, right? You can just check it in the Moodle. So it's totally about how do you simulate these kind of particle problems. You can take part in if you're interested in that area. Yeah. Another thing which we will be looking at today also is optimization. So there are three types of optimization. One is sizing, other one is shape, third one is topology. So the sizing is the easiest one compared to other two. Shape is next hardest. Topology is the most hardest basically, because in the sizing you don't change the shape. In the shape optimization you can change the sizing. What do I mean by sizing is basically cross-sectional area or thickness, cross-sectional area of a beam or shell thickness. Basically you can change them without changing the shape to do optimize for the weight example, so that you can reduce the weight of a component and then have the same strain energy. And then shape optimization means you kind of allow the beam coordinates to move so that beam also changes along with its thickness. That's shape. This is one of the advanced examples. And the topology means you don't even know how many beams are there. So you can introduce new beams or remove beams or elements or everything. So that's the hardest one. So you can see in the top right. Okay, the animation is not playing. Yeah. So you see after some time, yeah. So it removes elements and then build this bridge structure which has some other boundary conditions. Yeah. Yeah. Then there's topology plus shape optimization. Also, it's a different field of study and it's research area also. So this is about optimization. We will be looking at one of the Kratos examples on the hands-on session also in this regard. Yeah. Then you have the coupling. In here, I'm not talking about coupling with different physics. That can be one. But there can be different method couplings also. Like in here, MPM DEM coupling. You can see the particles are MPM, and then you have this box like in this one. So wait, I will just show the laser pointer. So in here, you see these are mpm particles, and these are them. How do you couple? Yeah. And in here, it's called chimera because if you think about this kind of large, so it's a fluid and structure interaction. And you have large, so this beam or whatever is moving around, and since it is moving around, it has large deformations. Then your mesh, no mesh can basically kind of remesh it to converge because the measure will be going crazy and will crash. Because of that, there's this something called chimera method, or there's another method called embedded to do fluid structure interaction with these large deformations. Yeah. This is that example, which is fully done by Kratos. All of these are fully done by Kratos, and this is the contact mechanics, which is again fully done by Kratos. Like to see how the contacts are happening and when does a contact happen and how the forces are reacting to each other. You see here, basically. Yeah. Next is basically some additional stuff. So we have reduced order modeling capabilities also, especially linked with neural networks. If you're interested, we can point to the right guys who are developing these. They are from actually from Simne. And then you have this kind of simulations also advanced debris flows also you can simulate with Kratos. Okay, this is repeated. I just want to show. And then this is another example which I want to show in the right one. The click to cast. This is one of the official industrial solvers offered by Altair. And how they do these simulations is actually backend, they're running Kratos. Yeah, you will see some problems in Kratos, which why it is open source, sorry. And then why they can do these kind of things and sell them also. I will show you the difference a little bit later. Yeah, so this is one of the most hardest ones because it has phase change, multiphysics, thermal, solid, everything included in here. So this is one of the hardest simulations to do actually in multiphysics, even to converge. But Kratos can do it. Yeah, to do it is also like making that case is also a bit hard unless you have the Altair tools because you have to write a lot in your settings, setting up the case. Okay, now enough with the propaganda, I would say, Kratos. I don't want to bore you. Let's start with the actual stuff for today. First thing is where to find Kratos. So I will just close this. Okay, how can I close? Eh? Oh yeah, okay. So now I'm going into basically the duplicate mode because I need always to use the same screen. Yeah, again I have to share. Yeah, now you're in duplicate mode. Okay, fine. First thing is where to find Kratos. Easy. You go to GitHub and search for Kratos Multiphysics. So this is the Kratos Multiphysics. Okay, how can I remove this? It goes away. Yeah. So this is where you can find Kratos in GitHub. So as I said, it has around 166 contributors maybe, but not everyone is active. Yeah, there are a few active, like around 100 and 110 active guys. So basic things are, if you're interested in the license, BSD, but I don't think you are interested, so I'm not going to talk about it. And its minimum level of C++ is 17, and it supports at the moment Python 3.8 to 3.12. But we will get rid of Python 3.8 because Python 3.8 has reached its end of life. So there's 3.14 also, I think now. I didn't check, but for the time being, we are having 3.12. But yeah, it's a matter of fact, we are supporting others. So you can see some of the main features in here and some of the example users, and that's contributors and users basically. Yeah, Bus, Siemens, Onera, and all of these things, and how to cite also if you are doing something with Kratos also there. So this is the basic place where you can find information about Kratos. In here, so if you have any question, you don't need to be in the Kratos community, you can use issues. Even though it's a small question, just put it in there because it might help others. Just put it in there. It doesn't matter. So whoever sees the first will answer. That's how the Kratos community goes, basically. If someone sees it and he knows about it, he will answer. If he does, because as you saw, Kratos can do a lot of things. And none of us are experts in everything. So all of the examples which I showed you, not done by me. It's done by a lot of others. So we are not experts, basically, but we are expert in one area maybe. So if I see a question related to that, I will answer. Or otherwise, someone else will answer because it's active community. You can see, yeah, the issues are 3 days ago, 19 hours ago, like that. It's happening super fast. Carlos is changing super fast also. But the basics are now converged for last 2 years, I would say. So basics hasn't changed, but new features are coming every day. So this is where you can communicate to us, or you can write to us personal emails also, because you know our emails. No problem. Or for Toon guys, you can do Teams chat. No problem. Also. Yeah. Yeah. And this is the issues page, and this is the new features, pull request, which we call. If you're not familiar with GitHub, this is how you can put a new feature request to the Kratos. It's called a pull request in GitHub. So you can see here, 9 hours ago, we opened like every day something, like maybe more than 10. And you see that, yeah. So last one is 15 hours ago, and we had a release also like, okay, it's not here yet because that will be there for you when you install it now. There's 10.3.2 now, the Python, but you will see it when you install anyways. So this is basically the issues and pull requests, but if you like, you can have discussions also. It's categorized, but most people prefer issues. Yeah. So this is where you can find Cardos. And let's look at the documentation, which is not our the strongest point at the moment, being a research community, because every one of us who are contributing to Cardos is mostly a researcher who has to do his research as well as coding Cardos. So then when it comes to documentation, that's where we are trying to push hard now, and also trying to push hard actually documentation, because we did a lot of things over the last year to improve documentation. You can find the documentation in here, basically. Now I will go back to the presentation just to show you levels of documentation. So for the documentation, you can just use GitHub pages, which will be deprecated in the future because we are not going to maintain it. But the best place is application interface, API. Sequence diagrams I will come later. Or you can look at the source code, because all of the new codes which are getting introduced to the Kratos, we are trying to put two types of documentation. One is Doxygen. We are trying to put Doxygen docs everywhere now because it's now becoming a habit. And then the best place to look at documentation is tests. Why I'm saying that? Because when you put a Doxygen, then you change something inside that function, but you forget to update Doxygen, there's no check. Only a human can check it and then say, okay, update this. Because Doxygens are not even compiled, so they are just comments in the code for the running time. But the tests is different, because unit tests, we have, I don't know how many, maybe 4,000, 6,000 unit tests in the whole Kratos. They are always run whenever you do a feature request. That means unit test needs to be always updated, because if single unit test fails, you're not allowed to put that feature in Kratos. That's how it works. So that's why checking unit test makes more sense, because it's fully up to date. Because let's say that I'm making a pull request, new feature, and it might break your code. Then I had to fix that in order to get my feature into the master, or what you call the mainstream release, basically. So that's why unit tests are fully up to date always. Then there's an example repository. I will show it now. So if you go back one, in Kratos Multiphysics, there's examples repository. Okay, it takes some time. It takes a lot of time. I don't know. Yeah. Yeah. So you see, for different applications, there are a lot of examples in here. So if you go for, I don't know, any structural mechanics application, so you have here different types of examples, validation and use cases. So you have eigenvalue analysis, so there's explanation and some animations like this. So you can copy paste and run these things. Just for an idea, so the basic explanation is given, and then you can see how it works. I will show you also today how to get those things. Yeah, this will. Yes. So now, so I just explained this. Okay, I did not go to this link actually, so I will just go there and they show it also. Uh, the documentation of the Kratos. Yeah. So this is the, I would say, the user level documentation, which we kind of decouple from the Doxygen. That means this documentation usually has the element formulations or whatever the formulations, but not exact details how it is implemented. Because we want to couple this exact detail and the actual physics, because physics usually doesn't change. Because if you look at the reality, it doesn't change basically how it reacts. But how we implement it might change due to our experiences, due to new features in the programming and everything. So we decouple them. So that's why we have the oxygen, which is commented on the code itself to follow the code. This is basically giving you a rough idea about how everything works together and what are the physics being used. So this, I would say, is a little bit long lasting than the oxygen. Yes. Yeah. So after this course, if you're still interested, you have here a crash course also. Again, you can follow some steps, which are, I'm not using this crash course today. I'm using a separate one due to the time constraints. This needs a little bit more time actually to do everything, but you can just go through it also. This explains step by step, which I will be also covering in a different manner. And so that's how to get Kratos also if you like for Linux and Windows. And macOS support is coming pretty soon at the moment. So do we have, you only have Mac, right? Yeah, there will be small problem with Macs because Macs have giving us hard time always, not like Linux and Windows, to be honest. Yeah, but we kind of fixed it yesterday night, but we couldn't put it to the Python package manager yet, an online version for that. I'm not sure for the Macs. Maybe you have to get help with others somehow, because you need to compile in Macs to get Kratos. You cannot use the Python install basically, because everything for the Windows and Linux, it's not a problem. You can just, I will show you, just you can use just Python. No, nothing to compile. Yeah, that's why I put in the Moodle also. Macs will be a little bit problematic actually for us. Not in the future, but for now. Yeah. And then you have here different stuff you can just check. So if you look at the source documentation, yeah, this is what I talk about Doxygen. This is basically automatically generated looking at the code and looking at the code comments. So uh, this is the next level of documentation for you to get information. So if you want to know something, so let's say that, I don't know, Beam, yeah, you get all the Beam stuff, basically what is available. Beam element is there, so you can see actually, but this is basically a little bit advanced documentation here. So it explains how every method works. So this is basically for the C++ level programming and advanced Python programming. And this one is for just understanding Kratos. This is two levels of documentation. So for some optimal applications, you have good documentation. Some still we are work in progress. Yeah. So this application has full documentation actually, but even though it's not physics, that's why it's easy to write. Statistics. Yeah. So you can just check it. Some applications still work in progress. Yeah. Yep. Yeah, this is the link for that. Yep. So that's it about the introduction. Any questions up to now? Or does anyone has any problems downloading the links basically? Okay. If not, okay, I can continue with the rest of the presentation. Okay, the pipeline of Kratos. So how do you do a simulation with Kratos? So it needs a lot of ingredients because simulations are complex, basically. So if you look at the pipeline of a simulation, this is taken from one of the literatures actually. So these are the basic steps which you need. First, you need to create the models and measures. That's a must in any software. It doesn't matter. This is common for any numerical software. It can be ANSYS, console, whatever. So you need to follow these steps anyways. So first you create the models and measures, and then you need to create the simulation parameters. What do I mean by that? Maybe inlet velocity for a fluid problem or a force in a structural problem. So you need to create the simulation parameters, basically. And then customizing the simulation run means maybe you want to add not the standardized versions, like constant inlet velocity. You want to add some curved parabolic inlet velocity. So customizing. How do you do customization of simulation run? So that's the next step. And the third step, fourth step is running the analysis. So how do you run? As I said, you can run it in shared memory in one computer or in parallel in thousands of computers, because big simulation needs big computers basically. Otherwise, you need years to compute the result basically. And then the last but one of the important steps is post-processing. How do you get the information of the simulation and how do you visualize and then make some meaning out of it? Because in the numerical simulation, you might get millions of values. How do you make something out of it? So that's a post-processing. Otherwise, it doesn't make any sense to do simulation also if you cannot make something out of it. Yeah. So let's look at how Kratos does it. First thing is, for the creating the models and meshes, you can use GID, which I will be showing. We will be doing it together. Then you can have GID is basically the free version is there for 10,000 elements, I think, for everyone for unlimited time. Otherwise, you have to pay. But we have the open source version, Salome. That's why I put that link also, because it's fully free. And it has, I would say, a lot more support community, because it's also developed by community, and it has a lot of features, which I will be showing some of them, because this is not about Salome course. It's about how to use Salome with Kratos, basically. Yeah. But you can have, there's a lot of Google, YouTube videos which you can see how to use Salome, because Kratos doesn't use anything specific from Salome. It's just normal Salome output, which we use. Yeah. Then we have some industrial ones like Siemens NX for Kratos pre-processing, but it's paid, and I don't know the price. Yeah. And then for creating the simulation parameters, we use JSON. I will come that to a little bit later if you're not familiar with it. What is it? And for customizing simulation, we use Python basically, because you can think of Kratos Multiphysics as a library like NumPy or SciPy in Python. It doesn't have any execution points. That means you cannot say run Kratos, something like that. No. You need to use a Python script always to run a Kratos simulation, because Python script is the guy who kind of governs how Kratos stuff is connected together and how they are executed. So Python is the governor basically for us. And since Python is super slow, that's why we have C++ backend, so that all the heavy load is taken by C++. But everything is exposed to Python, so you can call it like that, and then you can execute it faster in shared memory or distributed memory. So that's what I talk about C++. That's the deepest level of customization if you want, because if you think about it, if you know the source code, maybe you can do anything basically. That's the deepest level of customization, because you can just compile it and run it. As long as it's correct, it will run. Then, as I said, running the analysis, you can do MPA. That means distributed memory. That means thousands of computers running together. Or OpenMP, that means shared memory, running in one computer with multiple cores. For the post-processing, again, you can have GIE. You can have ParaView. That's my favorite, basically ParaView. Yeah, it's the open source one also, and it's good to know, because most of the softwares, like commercial ones, also support ParaView output, because it's open source. And again, we have Siemens NX, which is for sure industrial and paid. Yeah. So this is the full pipeline of Kratos, how you can do everything. Let's go to some of the sub-steps now. Yeah. So first, let's look at these 3 steps, because these are the easiest ones to do. Yeah. Now comes the hands-on session. So my talking part is finished. Let's try to do this problem plate with a hole using GID. So what we will do first is with GID as it mentioned. So does everyone has GID installed? Ricky, can I have your mouse? Sure. Yeah, now let's go to GID. So first thing is, so you have some steps in the slides also if you download. So open the GID first. Yeah, it doesn't matter the version. I'm not sure which version you have downloaded. For this example, it doesn't matter. But the interface might be a little bit different if you have a different version because there are a little bit latest versions than my one. Because I did not update my GID recently. Yeah. First thing is you need to do problem type internet retrieve. If you don't see Kratos in here, I don't think you see, right? In the data problem type, does it? No, yeah. Then go to internet retrieve. In here, find Kratos and retrieve module. It's in the data problem type. Here. Got it? And then did you find the Kratos? Yeah, then do the retrieve module. I already did it, so I cannot do it again. So it should download some things and fix some things for you. Yeah. Does everyone does everyone has this Kratos now? Once you have it, you should have this, right? Maybe for macOS, maybe there's a GID. I never checked. Let me double check. Mm, So it's not a problem because we are the ones who are developing, so we can kind of guarantee so no security issues in that one. Yeah. So for GID part, you can follow, and Salome part also you can follow. I think Salome is also there for macOS, I think. Only problem is the afternoon session. Yeah. Okay. Please go down. This one doesn't go up. Okay. Ah, yeah, it goes up. Okay. Hi. Morning. Yeah. So you now go to problem type Kratos. Yeah. So you will get something similar, but not exactly the same unless you have the same version. Maybe there's something more, something less, depending on your version. For the plate problem, we will be using structural. So you can use structural and 2D. Because this is a 2D problem which we will be solving, not 3D one. Here. Like this. So now you get this additional side panel, which is to like configure your problem. Before configuring, we need to have a geometry first, basically. So how do you create geometries? So if you look at this panel, you have here line, create arc, create NURBS line, and then this creates some basic geometries like that. This is how you can create geometries, even the 3D ones, like in GID. Yeah. how you create these geometries is different in every application. So you will see it when I do the Salome example also. So since it's a plate, so let me go to the plate. So we have here 8, let's take meters, and 6 meters here. So everything in meters, even though it's a big plate then, who cares? So you can create here basically a rectangle by clicking on this and in here. All of these steps are in the slides also, but you can just follow me in the screen if you're easier. And then if I'm going faster, just let me know. Yeah. So click on this. Then you see here at the bottom some instructions. That's how you follow in GID. So enter first corner point. So you here in the command, you can say XYZ coordinates of the first corner point. So this is, since this is 8 by 6, I will use -4, -3. If you don't give the Z coordinate, it's 0 by default. So -4 and -3 because I want to have the center at 0, 0. So here, now it put the first corner, then you can just either click on it, or you can be specific and put the here, enter the second corner point. So all the instructions are at the bottom. So you see what you have to do next. Either click or put 4, 3 for me, so that you get the box. Now you get the box rectangle basically. Yeah. Then again you see enter the first corner point. That means you can keep on creating rectangles. But since we only have one, to exit from this command, you press escape. Now here it says leaving no changes. So you exited from the rectangle creation process from the GID. You can zoom in to the area which you are concerned in by looking this zoom frame. And then I think you can just rotate or like translate by shift and right click like this in GID, and then rotation is left click. But you need to press the shift like this. You can always get back to the normal thing, like in view XY original plane in here. So click on here, XY plane. So you get to the normal. In GID, so the points are in white. Lines are, I don't know, this color is blue or what? I think it's blue, I don't know. This color. Yeah, and then the surfaces are showed in this purple. Purple says it's a surface. And bright blue, the volumes. It's bright blue or, yeah. But we will not be doing volumes in this one, so we will not see. So that's how you differentiate the lines, points, and surfaces in GID. But if you want to see the full flat view, so you can click on here, render flat. So you see it's just flat. So you see actually outer appearance. The problem is with outer appearance, if you have a complicated shape, you cannot configure like boundary condition is hard. So that's why we don't use this outer thing unless we want to find some problems in the mesh and all those things. So you can just change it, render smooth, and then again back to render normal. So usually we use render normal. Yeah. Now we want to create a circle in the middle point. So you can go here again, and here the circle. It doesn't pop the, yeah, circle. And here enter the center for the circle. Here it says. So you can say here 0, 0 because my center is that. And what is the normal direction of the circle? So for this case, it's positive, is it? Like this. So then, yeah, it's there. So you can click on it. So because it asks for the radius, or you can click or give the value. Radius is 1.5. Just give the value. Yeah. Now again, it asks for the same command because you can keep on creating circles if you like, or press escape. So you leave it. Now you might think that you have a hole, but that's not true. That's why we have other window also. So you have two overlapping surfaces. We need a hole exactly to be FEM because there are FEM methods which you we do overlapping measures, but not in this one. So we need to create a hole. How do you create them? There are multiple ways. There's no one way to do it, basically. One is you can use these surface Boolean operations, intersection, subtraction, if you like. You can try it by yourself. I'm using the easiest one, basically. Another way, at least for me, which is the most bulletproof way, what I do is, just to show you also the other options, basically, I will remove all the surfaces. Here you can delete points, lines, and surfaces in here. Remember not to tick this one. If you have ticked this one and remove something, that means it will remove all the lines and points if they are not connected to anything else. We only want to remove the surfaces here, not the lines and points which it's connected to. So untick this and remove these two surfaces, like clicking on this. So it says added new surface to selection, like that. You see whether it's working. Then press escape. So two surfaces are gone, but lines and points are there. Now I will create a surface bounding these edges. How do you do that? Click on this, create NURB surface, like this, and click here, enter the lines, define NURB surface, so it's asked. Click on these lines. Or you can select them by dragging it and putting it in a selection also. Then press escape if you have finished selecting everything. Yeah, it creates now something similar to what you show in the render view earlier. Okay, it's again also enter line, so I'm just exiting the NURBS creation, again pressing escape. So now I'm outside the NURBS creation. Still, it's the same from the render mode because you see a rectangle and a circle surface. But now that's why we need to have the other modes of visualization also. If you use flat, you see it's a hole. Yes. Yeah, I will do it again then. Give me a second. I will just delete this surface. So you go here, create NURB surface. Do you see it? Click on it and then select the edge lines. This and press escape once you finished. Yeah, now you have it. Then again press escape to exit the NURBS creation. Otherwise, it keeps on asking always to how to create surfaces. Now that's why we use flat. Now you see a hole is there. Nicely what we wanted, basically. Now we have the basic geometry. If you want to have 3D one of it, basically, you can do, it's not so intuitive. What you can do is, you can do utilities, copy. I mean, not for this one, I'm just showing it only, because this is a 2D one. You can do here, surfaces, here, extrude, mirror, everything is there. So if you want to get 3D ones from this. For this one, we don't need because it's 2D. So it's okay. Yes. Now we need to identify some domains, basically, to say, let's say, boundary conditions. Another small question. So everyone has some background around numerical methods, right? Yeah, so I don't have to explain that big. Because you can have in this example, we know left and right is fixed, and we have a load at top, a distributed load, right? So what we need is basically, we need to have these boundaries separately so that we can apply different things to them in the future. How do you do that? If you don't have the right panel, you have to click on this. So it pops up the right panel. The layers and groups, the button in here. Then go to groups, because layers are used to do the advanced modeling, so you can turn off and on some things and then use the visualization within layers with different colors. So see, to do advanced modeling of a little bit complicated components. The groups are used for the simulation purpose, to specify some areas to apply maybe some boundary conditions, or maybe some material properties, whatever you have to apply differently, the groups. Let's say that you have this plate half divided with two materials, then you need to divide first your mesh for sure, the geometry to represent that, and then you need to have multiple groups. So let's see how the groups are done. Right click on it, new group. Then I will just call it solid because this is a solid plate. You can just give any name. In this naming, you can use underscores. Dashes are okay but not recommended. Spaces, never. That's one rule basically. Since these programs are made to work in Linux also, the spaces are not friendly with us. So even though Windows is friendly with spaces, Linux is not. So never use, even in your folder directories, spaces. Because there might be some errors which is like giving some totally different error than what it's supposed to give, that using space is the problem. So even in your working folders, when you save these files, don't use spaces, use underscores. That's a best practice. I would say it's for most of these kind of numerical softwares, because those are research ones, mainly developed for Linux, because researchers are usually doing these things in Linux. So spaces are not friendly for us. So use underscores always, that's better. Dashes are okay, but not so nice. Yeah. Now you create a group, but you need to assign something to that. So you right click on it, and here assign. And it says points, lines, surfaces, volumes, or all types. In here, we would like our solid is a surface, so we say surfaces. Now it says here enter surface to be assigned. So you need to select. I'll just click on it. So it's selected. If you are in the render view, the lines view, which is not the flat view, then you need to click on the purple lines, which represent surfaces. Yeah, purple lines. If you are in the flat view, you can select anywhere in the surface. Now it says added one new surface. You can keep on adding to this group multiple surfaces if you like, or press escape because we only have one surface. Yeah, it says here assign one figures to group solid. Yeah. Then you need the boundary conditions. Again, a new group. I would say left edge. So you can say right click, again assign. Now it's a line, not a surface anymore. You can say line here and click on this line. So added one new lines. Press escape, done. Now I will move to the other mode just to see the other one. Now you need to do the same for the right edge. Assign line, so you can click on this one. That, and then the load. Yeah, like this. So for this example, it's not like that crucial to check whether what you have done is correct. But for complicated ones, it might be. Because you may never know that you have clicked on the correct line, because you might have visualization problems when you're clicking, and you might have clicked the wrong one or not. Because if you run with the wrong boundary condition, you will still get some result, which you will be scratching your head then, why it is like that. So it's better to always check your steps. How do you check that? You can use this light bulb to turn on and off. That's what I usually do. So when I turn off the solid, you see the surface goes away. Okay, that's the only surface then, which I selected for the solid group. You can turn on and off. So you turn off that. Then you turn off the left edge, you see the left edge goes away. So I have selected correctly. I have not missed anything. That's what I'm checking now. And the right edge, correct. Load, correct. I don't care about others. Basically, we don't have any, in this problem, we don't have any boundary conditions for them. We don't care. So that's how you check. And the other thing you can check is you can right click and list group entities and then see how many servers are there also. It shows how many surfaces. Only one surface. And the left edge, also the same. You can double check that. Whether you have here one line number is 4. That's what I say. It's one line because it is numbered, the fourth line. Like that, you can check whether you have unwanted lines also there. Because there might be some mistakes. So you can check here, the line 2 is there, one line, second line. That's the number ID of the line. Those are the same. So this is a good practice to check all this. Yeah. Now, next step is saving. With GID, saving is super important because it there are some things which might happen like crashings. Yeah, so it's always safer to save every step, not to lose the data otherwise. Yeah. So you save. I will save it in desktop. So I will just say this plate with hole. As I said, no spaces, underscores. Save. Now you have saved it. The next point is basically now we have identified the domain separately. We need to give some meaning to it, physical meaning. How do you do that? By giving this information basically. So first is model information. So it says the solver type is static. You have quasi-static, dynamic, eigenvalue, form finding here for different type of problems. When you change it to dynamic, here your settings changes. If you change it to other one, form finding, again changes like that. It depends on the, because this is the root setting defining a problem. So depending on what you are trying to solve, it changes the settings. So our case is static, so I will go with static. And then you have here nonlinear, linear. Yeah. This case is, we are putting it in nonlinear. Yeah, that's it. So that's the basic information about the model. Then this is the parts. Parts means basically the in 3D volume domains, in 2D surface domains. Basically the basic integral in your strong form, basically volume integral. In 2D, it becomes a surface. That's the parts. So you can have here solids in the parts, or beams, or trusses, or cables. Yeah, just a small reminder, the GID or none of the GID or the Siemens NX that which showed you that it has pre-processing capabilities are not covering the full spectrum of Kratos because the interfaces cannot keep up with the developments in Kratos. So these are subset of what Kratos supports. Like some applications are not even in GID basically because okay, the researchers doesn't have time to make interfaces because we are kind of working with always notepads to create the JSON files, which I will show you later. That's how we are working, not with clicking and stuff. We only click to create these geometries basically in our practical day-to-day life. Just to create geometries, we click and do this because otherwise it's hard. But for creating these files, we don't use interfaces usually. Yeah. So this is a solid one. So you can either double click like this to create a new solid. So its small displacement is fine for us. A linear elastic plane strain is fine for us. So these are the strain types and these are the element types. Again, not the whole spectrum of elements in Kratos. Kratos has a lot more elements than this, but only the interface supports this. The GID only supports this. And then these are the properties. You can keep them as it is. It's not a problem. And then you need to select which group. So we said solid. So we put solid and press OK. And again save. Every step just save. It's a good practice in GID. We don't have any beams, trusses because you can have multiple types of elements also here connected to each other. Like in a steel bridge, you will see that Like you can model it with beams and bottom with the shells. All of these things are possible, but to keep it simple, I didn't plan on doing that in this onboarding workshop. Yeah. Next, the time intervals is for transient simulations. For static cases, we don't care what is the time interval. We just use one time step. Basically, that's it. For static cases. Initial conditions are again for transient simulations important. For static ones, we don't care. It's good to have close enough solution, then it will be faster enough if your problem is fully nonlinear. The initial conditions matter. For the static case, this is a super simple one, we don't care, basically. Super simple ones, you don't have to care about it. This one you have to care, the boundary conditions. Depending on the type of the elements you use, like if you use beams, you will get some additional boundary conditions here, like rotation ones, because beams uses rotations. Or if you use shells, in 2D you don't have any shells. Only in 3D you will have any shells, because this is a 2D one. That's why you don't see in here shells. Shells are only available in 3D. So in that case, you will again get rotations and some other stuff also. Depending on what you select, everything changes. So in here, we only have displacement. We don't have contacts. So we don't need to put contacts here. So double click on displacement. So by value, I want to fix both sides to 0. So x is 0, y is 0. In here, you can put by function also. Then you can give a function. X, Y, Z, T are the parameters. X, Y, Z is the spatial coordinates. T is the time. You can give a function also here if you like. So here, x, y, z, t, those are the only variables you can use. You can use sine, cos, those things for sure. Sine, cos, all the geometric ones which are there, like tan-ish, all of these are fine. ABS, max, mean, those are fine. The variables you get are x, y, z, t only to execute this. We don't need this, so we will just do by value and 0, component y, also by value 0. Now you have to say where to apply this. I will say left edge. Press OK. So left edge, it's applied. Again, you need to apply a new one. So you can right click or double click. So I will just right click here, apply to entities. You can click on it. Then again, the same values for the right edge. Choosing lines and points. Actually, so this only works if you want to say here, new group and select. So if you want to, let's say that you forgot to do this grouping. Okay. Then what you can do is, you can just say here lines or points in here and then click on select. Let's say lines, select. Then you can select on the model bar here, the domain basically, like this. The problem is then the naming is automatic. It might mean something, it might not mean something. Yeah, you can do this. So then now press escape. Here it created displacement auto 1. For me, it doesn't make any sense basically. That's why we don't use that here. That's for if you forget here or you don't care about naming. So I will not use that. I will use the right edge here. Yeah, that's the difference in here. These buttons. So right edge. Yeah, cancel. I will just okay. Cancel. Just delete. Okay. Apply to entities. Right edge. Yeah. So you now see that two boundary conditions are there in displacement. Save. Always save. Yeah. Next one is the load. So you can have self weight if you like. Then you need to give a direction and everything. If you double click on it, you will see here the modulus and the direction. And the time interval is fully total for us always in every boundary condition. You might have seen here, time interval is total. That means because static cases, it doesn't matter. For transient, you can have this boundary condition changing over the time. So that's why your time interval is there. If you want to have that, you need to create here time intervals, new ones. You can create new time intervals to have different behavior, different blocks of time. Then you can use these functions also if you like, it's up to you. This is the customizability which GAD offers in the GUI. When we go to the Python level, it gives better level of customizability of doing these time intervals and everything. You don't have to stick to this. But this is click and run, so That's right there, like that. Yeah. Now I don't need the self-fit, so I cancel it. So we need load on lines because it's a distributed load. So you click on it, or right click and apply entities, or double click on it. It doesn't matter. Then here it says Newton per meter. Okay. It's 50 kilonewton per meter, so you can put 50,000 here. Or 5E4 in scientific notation also works, or 50,000, whatever works for you. Oh, sorry, it should be in the modulus, my mistake. It should be in the modulus always, and the direction is this one. So this should be always a unit vector. Otherwise, there will be errors thrown when you run it. So direction is basically minus y. So I put here 0, and in here minus 1. So here xy is given. And it always needs to be the modulus of this direction vector should be always 1.0 or close to 1.0 if it is arbitrary one. Otherwise, it throws some errors. The modulus should be separately given. Yeah, again, sorry. Yeah. Okay, so now you say load here. Selected the group load. Okay, fine. Okay. So now we basically set up the domain information for the elements with the here. If you expand it, you see here element is solid small displacement and linear elastic plane strain. And then these are the density and modulus Poisson ratio. Even though density is not used in this problem, but it's still there. But these two are used, so fine. Then you can have pressure on lines if you like, but not in this problem. So we have defined the boundary conditions as well as the domain now. Now we have defined how we are solving it. So you can go to solution, expand it. In here, you have multiple things. First thing is the strategy parameters. That means how do you solve? Basically, strategy means in Kratos, I will come into a little bit details a little bit later, means how do you solve? I'm not sure how much are you familiar with the Newton-Raphson or these kind of methods? So that's what it means. What kind of a back-end strategy to solve? Yeah, and then the residual criterion is there. It's a convergence criteria, basically saying that your residual needs to reach some point of value, like 1e minus 9 or something, so that it says it's converged. Because these are nonlinear analysis, you always have to have a residual criterion, or whatever the criteria, convergence criterion, sorry. Yeah. So this is the relative residual tolerance and absolute tolerance. So I don't need to explain them. Then the maximum number of iterations 10. Yeah, since even though we are using nonlinear here, you will see this will converge in one iteration because it is almost linear. Yeah. So this is the strategy parameters. And then you have the parallelization. In here, OpenMP means, as I said, it's the shared memory parallelism. And MPI means distributed memory parallelism. So you can select how you want to run this one. In the default installation, you only have OpenMP because for MPI, you need additional softwares. In Windows or Linux, you need to configure them correctly. So we will not experiment with MPI in this course. Yeah. So number of process only is required if you use MPI. In OpenMP, anyways, it doesn't matter. It will use the maximum number of cores you have in your computer. In Windows, I have no idea how to control that, but in Linux, we have a way to control how many cores you use in a single computer. In Windows, no idea how to control that. And contact parameters are not there because we don't use contacts. Fine. Then next one is a linear solver. As you know, these are PDEs. So we are ending up solving at the end a kx equals f kind of situation. So we need a linear solver. If you use automatic, it will try to find out, depending on your formulations, what is the best solver for you. The thing is, sometimes the best solver, the criterions which we have is might not be smart enough. So sometimes it's better to choose by yourself. Yeah. Because the criterions are super, I would say, trivial, which we have in there. Mostly we try to use the direct solvers, the fastest direct solver, which is available. Because Kratos, okay, next first question. Do you know the difference between direct solver and iterative solver? Okay. Yeah. So direct solver is something like, okay, I can just write. Mm, eh, mm. So we have kx equals f. So somehow we need to find for x. That's what we have to do basically in numerical analysis. So direct solver is basically trying to do it by x equals k inverse f. Basically finding this k inverse is the direct solver part. In iterative solvers, so you try to do it by, so you formulate some residual, which is basically f minus kx, and then iterative solvers, xn plus 1 equals xn plus delta xn plus 1, like that. So you try to minimize the residual, r, it should be equal to 0, but it won't be unless converged. So you somehow find this delta x such that you keep on updating until the r becomes 0. That's why it's called iterative solvers. Yeah. Yeah, if you want to learn more about this, I would say there are a lot of FEM courses offered by our chair also, so you can just take them so that it's going to be easier for you to understand what's happening in the background basically. Because this click and run stuff is nice, so you can see some nice colorful images. But if you want to make out something from those and then understand what's happening in the back end, you need to know this kind of background also, like numerical analysis background. Yeah. So we are using OpenMP and linear solver. I just keep it automatic because this is a simple problem. We don't have to worry about that much. Again, save. Afterwards, we have the results. So what results do we need from this? Because as I told you in the beginning, numerical analysis can generate a lot of results. So we don't want to store everything because our hard drives can run out of space. That's practical. In some of the simulations which we do, like one simulation may take 1 TB also easily. 1 TB of important information, but we are not we are giving a lot of information in there. Otherwise, it's not enough our capacity in hard drives. For this problem, it's still not a problem. So you can say here on elements, what do you need? Outputs. On nodes, what do you need? So you can specify here. So we need reactions, I'm saying, on nodes. Reactions means basically the reactions, the word says the forces on the nodes. And there are two types of outputs. GAU output is actually, if you want to visualize the output in here, you can say yes. VTK output is for the paraview. By default, both of them are turned on. Yeah, now you can save. But you cannot still run this problem because you created boundary conditions and everything is fine, but you didn't create the mesh yet, which is one of the hardest actually in real life problems, creating a mesh in a complicated component. How do you create a mesh now? You go to mesh here. So you have options in here. You can create unstructured mesh. Unstructured means basically in 2D triangles or 3D tetrahedrons elements you can create. And then you can give different sizings and all those things in here. I will just do one. Or you can create a structured mesh. In a structured mesh, it's like in 2D, it's going to be rectangles, in 3D hexagons. But the problem is you cannot create structured mesh on every geometry type. You need to do some manual editings to even for this one to create a structured mesh. You cannot create a structured mesh for this, basically. You need to break it down to some other components and then create structured mesh. It's not impossible, it's doable, but it's not easy. The difference is structured meshes has the advantage that they can be more efficient in solving. That's why some people prefer structured meshes, if possible. Unstructured meshes can be used in any complicated geometry, but then your numerical solver will take some more time to solve because they are not efficient as structured meshes. So let's use unstructured because otherwise I have to break it down to some smaller components to unstructured, structured one. So let's do unstructured. So you can say sizing on points, sizing on lines, sizing on surfaces. So that's the sizing part. I will use sizing on lines. It's up to you. You can do anyhow. So sizing on lines. So they ask a size. So we know this is basically how much? 6 and 8. So I will just say here 0.2 on the, and then click on assign. Then you select the edges which you want to have 0.2 size elements. So, and this one, I will just put this one, not that one. This one, and this one, I will just put 4 corners. Just for no reason, just putting it there. Then once you added everything, press escape to finish. Now you added here, assign 1 line, 4 lines are done. Here it says assign size 0.2 to 4 new entities. So those are the 4 lines. So you can see the final summary. Yeah. Then if you want to assign a different size, let's say that I will just say for some reason 0.3, just to show you only. Assign. I'll just assign here. Just to show you only. It's not required, but just to show you. Then you can just escape here, assign size 0.3 to 1 entities. Like that. Then you can close. If you are finished assigning lines, sizes, close it. Now you are done leaving assign mesh sizes to entities. So you are done with the mesh size assigning. If you like, you can go to unstructured and assign sizes on the surfaces also. Then you again have to say the size. I don't know. 5 maybe. Assign this. I just put a surface in there. So it's selected the surface. Press escape. Again, we don't have any other surface like this close. One thing about these meshes is actually they don't always follow what you say. If they find out some conflicting sizing information, they go for it depends on how the measure is coded, mostly for the first sizing it reaches. Because if you think that we assigned a size 0.5 in this one, so this corner element, to satisfy 0.2 in here and 0.5 in here might not be possible. So they go maybe with their own decisions, basically. So even these are suggestions only, basically. It measures decision, which size it will take. So once you have this meshing sizing done, so you want to check it whether you have done it correctly. So what you can do is go to mesh, draw, sizes, and all types. So you see the sizes you have given. Mesh size 0.5 for this geometry, 0.3 for this circle, 0.2 for the lines. You see the sizes you have given. Again, save, don't forget, like that. You can check your mesh quality also once you generated the mesh. I will show you how. First, now let's generate. In here, you can say, I don't know how much you know about boundary layer. For the fluid guys, boundary layer is important because that's where all the velocity changes happening. So you can create boundary layer meshes also, if you like, for the fluid guys. And then, so you have the element type here. You can specify triangle, quadrilateral also. Since we use unstructured, everything will be triangle. There's no point specifying quadrilateral. Yeah. Yeah, there's mesh criterions. Those are advanced stuff, how you can just do the meshing. Yeah. Now, once you have selected and done the sizing correctly, click on the generate mesh. This is the general size which the algorithm will use, the meshing algorithm will use if you haven't specified any size for some domains. Okay. So it's also optional. If you have specified every size correctly, then this will only be used, basically. So you can say 0.5. Oh, okay. So it will generate the mesh. So it says linear elements means 100, that means the edge elements. And you have triangle elements, which are the surface elements. 764, nodes is 408. And there is the memory consumption, it's super simple mesh, so it's fine. So you can say view mesh, so you see this kind of mesh. It's not the best mesh, but yeah, we can work with that, basically. Now save. Now, how do you check the mesh quality? Because that's also important when you come to numerics. Because if you have a bad mesh, you might get an answer which might not be reflect in the true reality. It's always assumptions because when we do numerics, we do a lot of assumptions. So you need to always check your assumptions when you do numerics. So you go to mesh and then check mesh quality. Here, so for linear elements, it says, okay, you can check different quality criteria. Element volume is only one which is there for linear elements. So you see the volume, there's 0.2, 0.2, 0.2, 0.2, 0.2 everywhere. So it's nice. It's the same size every element, even though it's a cumulative graph basically. So it's a cumulative graph. So you can have here cumulative or normal. So everything is 0.2. So it's fine. Yeah. Then let's look at triangles. Okay, triangles is not the same case as I told you. It cannot have the same size measures. So you see here the volume is 0.19, but the problem with triangles is I don't like the volume that much. I usually use either the Jacobian or the shape quality or the minimum or maximum angle, basically because it makes sense. What does it mean by minimum angle is basically in a triangle, what is the minimum angle you get in every element? So if you have a perfect triangle, if every angle should be 60, that's a perfect. Then your mesh will not have any troubles at all. But in reality, you will not never have it. So you see here, 28.4 is the minimum angle you have, and the maximum is 59.3. So it's almost 60. So there are some elements which are 30 degrees, but it's not a problem because it's not a skew. If you want to see what elements are problematic, like if you find some, like say 1 degrees, that might be a problem. If you want to see, you can just double click on it, and then it will show all the elements which has a value below that. Yeah, these are the elements for the mesh quality control. Then you can just edit those elements manually by using here geometry edit, and then move those nodes or break it to multiple elements, all those things. Yeah, that's a little bit advanced, but you can just try it out if you like. So yeah, divide is there, join is there, all of these things are there for, but it's a bit advanced. Yeah, that's how you can do it. And then if you want to keep these elements in a different for the future reference, so you can just say send to a new layer. Like this, that's why the new layers are used. So you can say new layer, and then if you close it, if you go to layers, so you have here, this layer has the elements which you selected. Now you can work on them separately. Layers are used for this purpose, just to work on some sub parts, basically, turning off the others. It's not used by the simulation, the layers. Only for the geometric modeling and mesh handling, basically, the layers are used. Like that. Don't forget to save. I am repeating, that's because it's super important. The saving part with GIE. Yeah. Now we have created the mesh. Yeah. You can try run or calculate. I don't think it will run for you. Let's try it. In my case, it will run. If you say calculate, okay. Okay, I didn't save it. Okay, wait. Kratos mesh. Yeah. What is this? Okay, it says my file directory is wrong. Let me double check. Okay. The best way which I would always say is write calculation files, no run. Do that. It's easier. Because we anyways need the Python separately to do our rest of the course. Because I usually doesn't run it in GID for different reasons. So you can say write calculation files, no run. Oh yeah, that's a problem in GID. Did you were you able to do this? I'm Yeah, my one is broken, I think. That's why I told you GID is a little bit delicate. My one is a little bit broken. It was working yesterday night. Yeah, give me a second. I will just do everything new. Because sometimes when you have in between errors, GID kind of breaks and no one knows why. So I will just do it easy, super fast. This is settled, right? Yeah. Yeah, yeah, I didn't give any sizing, so it's like this. Okay, it works now. That's what I told you. It works now. So when you have some intermediate errors in GID, this can happen. That's why we always save and reload. So that you can reload at a earlier point. Another point is the undo is a little bit not so, even though there's somewhere undo, don't rely on it. Always save different steps in different file names and then use manual undo. Yeah, now it worked for me also in DP written, but I can, I think now call calculate also. It works. Earlier because I had some intermediate errors, so that's why it was not working. So you can say you're finished. But I don't think you can do it. Can you try it? I think you need to install Python not separately. Does it work for you, the calculate? No, right? Yeah. So let's go to that now. Fix that. So open command prompt like this, because this is anyways required for the rest of the course also. Yeah. So first check your Python version. You can say Python version. So does anyone has something about 312 Python version? So that might be a problem. No, right? And below 3.8 is also not there, right? Python 3.8. Because Kratos is not there for only for 3.8 to 3.12 only at the moment. Yeah. So if it is this, then what you can do is first create a Python virtual environment, because it's always nice to work in environments. Don't screw up your main Python repository, because these are it's nice always to work in environments. It's a good practice. So I will create one C software. I think it's capital because Windows has a problem of being case sensitive. That sucks in the time. Python, I have this folder already, so I will give a new name now. So this folder already exists for me. C software Python VNV already exists for me. Then now I will give Kratos onboarding a new name. So this is how you create a virtual environment. So it does something. Okay, text type. I might need a charger now. Otherwise, I'm my computer off. Yeah. Station is where Commander. No. And you don't see there. Yeah, thanks. Then I don't need this. Thanks. Mhm. Yeah, the command has finished. Yeah, it's slow maybe because I'm out of juice in my laptop. It's charging, nice. Okay, now the command has finished. So now if you go and look at your folder, so I will go there, see software, Python environment. So you will see some folder called Onboarding. It's created by the virtual environment of Python, so it will have some additional files like this. Yeah. Once you have created that environment, you can activate that environment by saying C software Python env Kratos onboarding scripts activate.bat. So whatever the name you give here, you can just use any name. Don't use spaces. Again, even Python might not be friendly with spaces. Underscores are better. And then activate.bat. So it activates. Yeah. So now you know the environment works. I'm not a big fan of using the command prompt like in here because it doesn't show us what's happening in the background. So it's activated, but it doesn't show which environment it activated because you might be working as you have seen. I have in this laptop 3 environments. In my actual working lab one, I have maybe 30 environments working in parallel. So you need to see which environment you activated. There are ways to check, but I would like to see it always. So what I do is usually I use VS Code. Now we go to VS Code. I think everyone has installed VS Code, right? Okay. So let's open a new folder. You know, samples. Yeah, yeah. Oh no, let's go to desktop actually. It's easier. Desktop. I just open the folder. Yeah, I always trust, so it's fine. And we don't need the Copilot for the time being. You can just use Copilot also for everything, but we don't need it for this course. Yeah. So now you, okay, I think I saved the last version as 1, right? Yeah. So I will delete this one not to get myself confused. Delete, delete. All right. So now this is one which we have run. Basically, how do we set up to run Kratos is there are multiple ways. First, since I told you the execution points are Python, you just open the first Python file. Don't look at the code yet. Don't worry about it. I will show you more simplified code actually. So just here. And then here at the bottom, you see Python 3.12. Does everyone sees that? Right? That's actually your environment which VS Code is using at the moment. You need to switch it to the environment you created. How do you do that? Click on this. And then browse. Okay. And then go for that directory. C, software, Python, onboarding, and then think scripts. Yeah, scripts. Then click on the Python exe. Click open. Now, yeah, it changes to Kratos onboarding automatically. Now, nice thing is, once you do that, go to, in my case, it's triple dot because it doesn't have space to show the rest of the menus. If you have a bigger screen, you might see rest of the menus. So rest of the menus terminal and open a new terminal. Now you see automatically which environment you are in. Kratos onboarding. That means this is automatically initialized with the Kratos onboarding environment of the Python. So VS Code takes care of it. That's a nice thing. VS Code is helpful in Linux also. Linux has a lot more advanced stuff than Windows for sure. That's why we are always using VS Code. So this is the one which I will use. Now, let's see, since I told you I will come to the file structure a bit later, explaining what's inside every file. Let's see first to see whether we can run something, because every time it's good to have something to grasp rather than me explaining something. So I will go to the folder cd plate with whole gid. So I'm in that folder. Now, if you try to run, how do I run it? There are multiple ways. So you can click on this, which is not my favorite, or debug also. There's a debug also. I am not a big fan of that. So I always go to the folder and say Python main console part. Usually. So this will execute the Kratos simulation. Let's see what happens when you press this. True. I don't have Kratos because we just created the virtual environment. Haven't installed Kratos yet. So it throws an error saying Kratos Multiphysics is not found. That's understandable. So how do you install Kratos? In the Python version, I'm just talking from the Python side. You can say Python -m pip install Kratos Multiphysics, like this. So press enter. It should take it from the internet. If you need to have internet for sure for this. Yeah, it will. So it has 10.3.2. That's what I told you. So in the web page, we haven't updated because this release was done yesterday night for this course. Yeah, it installed Kratos Multiphysics, but this is the doesn't have any physics, because I can explain the structure a little bit later. Just follow with me for this one. So now what we need is basically we need a structural mechanics also, because this is a structural mechanics problem. So you can install structural mechanics application also, like this afterwards. Or you can put everything into one line. It doesn't matter. So you can install the separate applications. Yeah. Kratos. Spellings are wrong. That's right. Yeah, that's the problem. They don't suggest structural. Yeah, they don't suggest correct spellings. Yeah, now it's installed. Yeah, the spelling problems are always there. So we have to deal with it. So yeah, now we install structural mechanics application. And we can live with those, but it's good to install one additional one for the time being, which is called the linear solvers application. As I told you, it has better linear solvers. Otherwise, Kratos also has inbuilt linear solvers, but they are not the most efficient. So that's why we have a separate application called linear solvers application. Okay, just install it. Okay, like this. So now you have basically, I think that almost everything what you need to run. Let's see, maybe I'm wrong, because I don't remember, to be honest. Let's try running it. Now let's run it. Yeah, it ran. Nice, no errors. So this is how the output of Kratos looks like. First, you get the release, the version, and this is the commit hash from the GitHub. It's kind of like a snapshot of Kratos. So you can always, so let's say that the problem with Kratos is it's always evolving. And you are making a test case, examples and everything, like a domain and everything for Kratos today. And after 1 year, you won't run it again. The problem is Kratos has changed 1 year, and then if you run this, you will get a lot of errors. Then either you can invest time in changing this to the updating it to the current version of Kratos, or you can just use this hash to get back to the Kratos version 1 year ago. Git allows it. Then you can run the same case without any problems. Like that. So that's why they reprint this hash also. And it's always good to keep these log files whenever you create run simulations in Kratos. In any numerical software, I would say, keep the log file, because every numerical software has this kind of time tagging, because everything is evolving. Yeah, it says 8 threads, because I'm limited my computer to use 8 threads. It might use the maximum number of cores in your case in Windows. And it's this structural mechanics. So this is the basic output. So I will not go into details of this one now. So it runs. That's the best part. Now let's see the file structure of Kratos. So as I told you, this main Kratos is the execution point. It's a Python executable. So in here, you see, you import Kratos Multiphysics. and do some things in here. So that's the execution point because it needs to do everything, reading, simulating, writing output, everything. Then I was talking about JSON files to customize the simulation. So these are the two JSON files which you have, but not always two. Like you will see in the last example of optimization, you might have maybe 6, 8 JSON files because they get complicated. Even in code simulation, you might have 4, 5, depending on how much multiphysics you are doing. So this is the most simple. So most simple is you will have two, the minimum. So in here, the first one is called project parameters. So if you look at this, you see some, these I just collapse these blocks. These are the main blocks in JSON. Yeah, so the problem data specifies the problem name. This is for your reference. We don't use that. To have a reference for you, like what this JSON file represents. And here parallel type, you see OpenMP or MPI. So to run in shared memory or distributed memory. And echo level, actually, if you increase, you will get a lot more prints type to debugging. Because sometimes your simulation might not converge, or sometimes it might crash without giving an error, giving an error and without giving an error also. That can happen also. So you can increase the echo level to see what's happening in background, so it will print more information. But if you go beyond 3, it might be unreadable also because it will print the whole system matrix. In the big case, it's if you have 100,000 docs, everything will be printed. It's started your log file. It's up to you. Start time and end time is static case, it's always 0 and 1. For transient, you need to have start time and end time. That's the basic setup of the problem. Then you have the solver settings, which are basically the linear solvers and all those things. And then you have something called processes, which you use for applying boundary conditions, and output process is for outputting. This is stage. So this is the basic configuration. Yeah, in the solver settings, you will have a lot more depending on the type of the solver which we will use. Like, as I told you, the time step, it doesn't matter in here. And in here, it's static, nonlinear, domain size is 2. That's whether it's 2D or 3D. And this is the geometry file input and the criterions which you use for as well, which we set already in the GUI. That's why I told you we are always working in the JSON level, not in the GUI for this. Because this has more flexibility. And the processes, you see here, we apply displacement, restricted boundary condition, constraint true in all 3 directions. For left edge, right edge, and we apply a load 50,000 in the -1 direction. So GID, what GID does is actually GID always translate all the GUI information to these JSON files. Because Kratos is not fully coupled with GID. Kratos can do everything without GID. It just needs a JSON file and the geometry file. Then it Kratos will run. Yeah. Then you have the output processes. Like, so outputting, this is for GID output. And then you have the VTK output for parameter. So what are the variables which you want to output and all those things. Yeah. Then we have a separate file for material properties. This specifies the material properties for structure. So this is the linear elastic plane strain 2D law, which we set in the interface. And then you have the density Young's modulus Poisson ratio, which we specify. So this is that. These two are those two files. And then GID creates something called MDPA. I'm not sure about actually what it means, the MDPA, but it's the geometry file. So it has nodes. So this is the ID and this is the XYZ coordinates. In Kratos, nodes are always 3D. The simulation can be run in 2D, but nodes are always 3D. That means the geometry file almost is in 3D, basically, but Z coordinate is 0. So in VS Code, you can collapse these so nicely, like this. Even though you have million, it might not work. With 100,000, it works. Yeah. Then you have the elements. So you have the first element. This is the connectivity. That means, no, this is the properties which we don't use anymore. It's for compatibility with the older versions of Kratos. these are the nodes which is connecting. We will be creating these files from scratch. Then you will see some important, I will say some important facts about these values. And then these are the line load condition because it's a distributed load. So it also has an ID. And then these are the nodes that's connecting 1 and 3 like that. Yeah. Rest is about the subdomains. Basically, we will rectangular that later. Now that's the basic file structure, and the main Kratos is there. Rest of the files are not used by Kratos. So if you like, what you can do is you can say here new folder Kratos only, and then you need only this, and this there. Copy it because GID might need it. So you only need these 4 files for Kratos to be clear. So you can still go Kratos only and then to buy the main Kratos. So it runs. Yeah, it still runs. Yeah. So these are the only files you need, these 4 files for Kratos, as I told you, JSON and a geometry file and the main Kratos for execution. Now let's look at the result. In GID, if you want to look at the result, you can click on this. Since we ran the simulation, so it should be fine. Here, it says pre and post processing. Click on this. Let's hope it works. Yeah, it works. So its interface fully changes. Yeah. So you can just zoom in like this, and then you can see visualize stuff. So in the displacements, you can see the displacements like this. Or if you want to see the components of it, so you can see X, Y, Z, however you want. And if you want to see von Mises stresses, this is the one. Von Mises stresses. Those are Gauss point values, so that's why it's discrete per element. And if you want to see reactions, so you see the reactions are higher in this 2 edges, that makes sense. Rest should be 0. Almost. Yeah, that's how you can visualize. Yeah, there are some additional filters and the mechanisms, so you can just check them out. If you want to see the deformation, so you can go here, deformation, and then click on displacement. So you see how the structure deformed with your load. And there's this multiplication factor for sure, because actually it doesn't deform that mean. This is artificial, I mean magnified deformation. Yeah. Yeah. With this, I think I'm concluding the GID part. I don't think I missed anything. Yep. Let me double check. Yeah. And then we can take a break of 15 minutes, I think, right? The break. I don't know when is the break, to be honest. Yeah, it's 9:45. Okay. I'm a little bit late, but it's fine. Yeah, we can take a break of 15 minutes if you yeah. Then if you have any questions also you can ask me like anything regarding up to now. Yeah. Yeah. Yeah, yes. Hi. Yeah, you can just yeah, yes.
We, I'm not sure if I can't able to view the becoming of the
Okay, first of all, we need to open the Python file. Open Python file. Yeah, go. You need to go to reality play.
and software.
Onboarding, and then go to script, and then click Python. Okay, okay, I will take you on the, I will install it. No, I think you don't have the extensions installed, which I will show you now. I can install it for you. You're changing, right? Does it come?
I'm not sure if it ain't even so useful.
Yeah. Okay. Maybe somebody would sleep under water. Yeah, it's fine. That is good. I think in that case, we may not treat maybe because it's so well. For the time being, I would say that it's by one it's fine. So then, but you won't be giving much. Sorry, maybe the Python version is also. Oh, you can do it by Windows. Ah, let me check what I have. Additionally, extensions. Uh, I don't have anything else to write. It's PowerShell. Maybe it's a Windows thing. I think what which Windows are you using? 11. Maybe it's a Windows PowerShell thing because this by default came to me. Yeah, but yeah.
I'm not sure now it's not coming.
Yeah, maybe you can restart and try. Yeah, it always does. I'm not sure. But you can follow them because everything works, only this it's not showing. Yeah.
What in the.
So you can actually you can just install this you have a password, you do
Ja, jetzt, ja, auch gut eigentlich, aber ich habe eine Monatabgabe. Ja, Dezember.
Ja,
Und
also dann
ich glaube, jetzt schreiben das weiter, weil die Anwendung hier ist anders.
ja.
Ich wollte einfach nicht auf den See machen und funktioniert nicht. Also die wollten
All right. You have a different. I think we have here different fine.
Weil das du quasi extern, also du nimmst quasi extern Python und führst dann für die Sachen, die du brauchst, Kratos aus. Ja, genau. Das ist richtig einfach. Ja, ich ja. Weil einfach viel, was du brauchst. Ja, du im Praxis drin. Ich finde ich voll von so also, was einfach nicht so die Idee ist. Also, die Tutorial ist. Also, man kann nicht, ich habe schnell die Gleichschluss angeguckt, alles. Ich habe mir alle Flavor, das sind die letzten Zeiten, wenn die so gratis sind, das ist von 2010 und 2013. Bro, wir waren in 2025 so.
Okay, you have the latest version of
basic was training and haben es halt wirklich fast mega. Ich weiß noch, wie vorne steht. Und dann immer so, ich sitze halt so daneben. Und ich will es mal wieder machen, aber es ist eng. Yeah, so
My version was this is the latest version because I don't have the setup because I'm not using GRE that much. Can you try downloading this version? 10.1.3D. It should be there. I think you have a latest version. I'm not familiar with the GRE part because I rarely use GRE. Yeah. Yeah. Hi.
another good question.
Yeah.
Very basic one. And waiting to the post so there's two phases of the.
Yeah, I can approve. Give me a second. Yeah. Yeah. I can.
I just registered yesterday.
Yeah.
You just told me about the course.
Okay. No problem. It's not today, right? 21st is not today, okay.
Sorry?
No, it's the maintenance. Yeah, this site is super slow.
Mein für dich ist super wichtig, du kriegst dann, weißt du,
Oh, there are more. Okay, fine.
how did you learn Kratos or how did you teach it to yourself?
That one I will tell you a little bit later. So how to learn Kratos. That's one point which I will come because with GID it's click and run, but it doesn't help much. I understand. That's why we have separate afternoon fully for that.
Yeah.
How to
leave.
but
still like
okay, then
I need
it's
to use for on a master. I probably
okay. So in that case, what I can do is I can send you the slides.
Yeah.
You can just take a look at the slides.
Yeah.
Yeah, maybe I will upload the video also because of recording it today. Yeah. So
Thank you.
yeah, no problem. Okay. Yeah. Hi. How are you doing?
Okay.
Yeah.
I just one can you also add me to the moody page because I'm not there.
Sorry?
Can you also add me to the moody page?
Yeah, sure. Participants enroll. I cannot write your surname.
Yeah, it's okay.
Oh, it's all.
No.
Wait, it's ready. Touched you this.
Yeah.
Safe, bad, safe.
Yeah,
Yeah,
writing
sure.
confusing because
I understand.
it's a bit
Yeah.
different from what I'm doing.
Yeah.
Yeah, with the optimization, I think it's also I've looked at the files, so they're quite different from that what I
Yes.
do, right?
True.
So yeah. Would you be like available next week somehow?
Next week will be free actually, so we can have a meeting
Yeah.
and then fix. I didn't have time to look at
I
the stuff
totally
and all
understand you, yeah.
because I think I finished this around yesterday 2 a.m.
Yeah, it's totally fine.
So yeah.
So then I text you. I
Yeah.
think it's the best, right?
Yeah.
And then
Yeah.
let's see, maybe
Monday I am not there because I'm on holidays, but Tuesday, Wednesday, Thursday, Friday I'm there.
Tuesday.
Yeah, Tuesday.
Let's see. Yeah.
Yeah,
Okay. Nice.
See you then.
Then I continue writing
Yeah.
and then.
Okay, see you.
Thank you.
Okay, bye. Why doesn't it come? I have no idea.
I don't know. But actually, it's okay.
I can send you the.
Leo send me the slides and so and everything.
Yeah, okay. In the worst case, you can use the guest access.
Yeah, I also wanted to ask.
There's a guest access.
Guest access.
How do you log out of this?
I think you need the password for it.
Yeah, the password you can go to it. Should see.
Do
Give
you
me a
remember
second.
the password? Because I know
Yeah.
how to do it.
Yeah. Let me just do extend. Then yeah. So to chat. I need to find who I sent it to first. I sent it someone. I didn't know. So this is basically the.
Thank you.
Yeah.
Yeah.
So you can use the guest password.
I also want to just now we're gonna do the Salome, right?
Yeah.
So I just need to install the Salome for just for Windows.
Yeah, you can. Everything I do today works in Windows.
Okay, because I think my Kratos is installed on Ubuntu 24.
Yeah. Okay. It doesn't matter. Then you can still run whatever you generate in Salome in that Ubuntu.
Okay.
You don't have to specifically get install Kratos in there.
Okay.
Yeah. So it's fine because Salome, as I told you, it's just a modeler, geometry model. That's it.
Yeah, exactly.
You can have Kratos in Windows, Linux, it doesn't matter.
Basically. All right, yeah. Then I will install it.
Yeah.
Hi, Sana. Will the recording be available in the Moodle or something, maybe?
I mean, in here, they are subdividing specifically into three. Usually, specifically, everybody, and the extra part, and comprehension. That's all three are sufficient. Even though, yeah, the shape of the room, so technically, government, yeah, yeah, but they have subdivided it further. They have four, yeah, yeah, then here in the focus on the test, people have two, English and Finnish. Especially all other three. Yeah, when you can they got it decided and by getting back, I came 1 year and 1 year. We did the whole patient. Yeah, I didn't know about this actually. So people don't need just get easy, right? Yeah, we have enough time for you. Yeah, and you the person who do the recording, so actually. Yes, you said. Yes, also, but it's a family channel. I want to take my main classes. Take my main part. Yes, yeah. Yeah, but this machine is what I think. Okay. Yeah, this always a chance. Or the first time or answer. And so you can read those two places. You just have to hold on. Something like this. Say, you saw in the morning, you have to sleep. You know, that we don't. And then after lunch, usually I got yes. Yeah. So okay, since everyone is back, I think we can start. Yeah. So now the GID session is over. Now let's look at the fully open source pipeline version, which is a Salome. I hope everyone has Salome installed. Yeah, so I will close TID now. Okay? Okay, I will save everything. And close. I hope this is still being recorded. Yeah. Yeah.
This machine done by the gig also from the Kratos software or?
No, this machine is purely done by Git. Kratos has its own measures, as you show in some cases. We are not going to touch that at the moment, but I will explain some of the structure in the afternoon session because afternoon session is fully for in-depth Kratos. Morning session, I kept it just for clicking and running. So that you are not getting overwhelmed in the morning, so that you're not running away basically. Yeah. Afternoon is fully in-depth Kratos in fully hands-on without clicking and running. Basically. Yeah. Okay, so we can close this for a second. I will just close this. Okay, I don't need this. It's the same problem. Just to see the differences, hardships, everything basically, because it's everything is like, okay, when you get something easier, you have to pay some price. It's always like that. Yeah, now let's look at Salome. So you have some instructions in the slides. I'm not showing it because I'm gonna do it online with you, so you can also follow me. But for future, you can just refer it if you forget some steps. Basically, that's why I put them in slide also with screenshots. You can see here, there are screenshots, how to select and everything, but I will do it with you now. First things first, everyone has Salome installed, right? Yeah. Let's open Salome then. I have 914, but I checked yesterday night, there's 915. I don't think it should be a problem, 914 or 915. Yeah. Yeah. So this is Salome. Okay, give me a second. I think I can magnify these things because Salome in Windows is a little bit like too small icons basically for the presentations. Let me try to size it. How do you change the text size? Text size or something? Yeah, yeah. I will try. I don't know whether it will work. Let's see whether it helps. Oh, it's yeah, it doesn't help. Yep. I don't know how to zoom. Does anyone know in Windows how to zoom?
Probably play them.
Huh?
Play settings. Yeah,
The magnifier. Okay, that will be hard. We can use the magnifier for sure. Ooh, then the navigation is a little bit hard.
play settings. There is a scale.
Okay, let me try. Brightness. Okay, I don't see it. Here, scale. Okay, then what I will do is I will revert the text size because it's going crazy now. Text size 200. Okay, that's nice. Okay, let's see. Let's close Salome. And then scale 300. Okay, let's see whether it works. It's like kids computer now. Everything is super large. Okay, it doesn't help for Salome. This one doesn't go up. Yeah, it's still the same size, right? Yeah, but I cannot help it then. Yeah, it's a something with the Salome's GUI. Yeah, we have to leave it that, but fine, I will just keep the scale for the time being. Yeah. First thing, Salome, as I told you, it's a little bit more sophisticated modeler geometry, and maybe for some softwares, it can do the simulation in itself. Like, I don't know, there's this code duster. which you can create everything in Salome and run the simulation also in Salome and do the post-processing also in Salome. But for us, we just use Salome as a geometric modeler. That's it. Then I will come to the generation of JSON files and everything later. Because geometry is the one of the hardest things to generate, because if you think about a complicated component, generating a mesh maybe takes weeks. So you need a good measure, that means good geometry modeler and with a lot of features. So that's why we have this open pipeline, open source pipeline like this. So when you go to Salome, you see some menus, fine. First thing is you need to go is Salome and Shaper. Keep in mind, this is not the only way to make geometries in Salome. There are multiple ways. You can even skip Shaper and directly go to geometry. I will tell you the difference when it comes to that point. Yeah. First, let's go with the Shaper, because for me, it's nice because it gives a lot more flexibility. So you go to Shaper, you get this kind of interface. Do you think I should switch back to white or should I be in black? White would be better or black would be better? I mean the background, basically this is black. I can try white actually. Dark. Yeah, dark. Let's try light. Okay, let's reset Salome. Nope. Is it better than the white one or the dark one, or same? Yeah. Okay, then let's not waste time on these colors. Yeah, when you go to Shaper, you get a lot of options, even though they are super small. Sorry about that. I don't know how it looks like in your computers. My computer is like this. Yeah, and Linux also the same basically. Okay, I get a chat. Okay. I am not sure how to do that. Yeah. Yeah, if you have any suggestions, just ping me actually, so then I can change it, because I don't know how to change the icon size in Salome. I tried it, but didn't work. Sorry about that. Yeah. So in the Shaper, first thing is, so you have here this object browser in Salome, which is kind of like the parametric modeler. Salome can be used to do parametric modeling. Even the mesh can be parametric. One nice thing about Salome is, if you want to do advanced parametric studies, whatever you do in Salome can be recorded as a Python script, and then you can run this Python script multiple times with different parameters. That's the best thing in Salome. Because backend, it generates also Python script. Basically. We don't see it, but if you look at the source code, there's a lot of Python scripting in Salome also. Yeah, so this is the object browser. So it has a lot of things. First thing is we need to create a sketch. That's how we started in GID. We created a 2D sketch, and then afterwards only we did the stuff. So how do you create a sketch? There should be a button, even I can see it. Or you can go to sketch menu, because there's a button for showing for sketch. But if you can't find it, go to the menu. Sketch. So it's visible there. So that's for sure a shortcut. I cannot see it now with this zoomed version, because all my usual positions of the icons are now different because of the sizing. Zooming. Yeah. Create a sketch. In the sketch, they ask for a plane. Since this is an initial sketch, so they will only show you 3 planes. But when you create more complicated geometries, you can use the surface as a sketch plane also of another component, like that. So initial one, they will only show you these 3. You can create custom planes also if you like in here. Another point in here is selecting a plane is a little bit important if you want to do 2D or 3D. Let's assume that you want to do a shell analysis in Kratos. In that case, as I told you, shell elements are always 3D. But if you do a shell which is just on a single plane, right? That means you just need XY, right? Basically. But the problem with Salome is if you do on XY plane only, all of your things and all the components are only in XY plane, not even extruded to 3D, when you generate the geometry file, Salome interprets them as 2D, then writes them as 2D geometries everywhere. Then when you read it in Kratos, shells are 3D. Kratos says, hey, you have given me 2D geometries. I cannot work with that. Give me 3D geometries. So if you work with shells and if you're only in one plane, you please select a plane which is not XY. If you use any other plane, YZ, XZ or whatever the plane, then Salome will write them as 3D geometries even though you are in a single plane. That's a trick. Basically, the thing is, if you don't know that, then if you do it everything, then you find out at the end, so you have a lot of time. That's why I'm telling you. This information is not there in anywhere basically, which we also found out by finding out the bugs basically. Yeah. Salome does it. We don't have source code of Salome even though it's open source. No one looked at the Salome code. Yeah. Now for us, we don't care because we are doing a 2D problem. So we can use, this is the XY plane, the blue one. This one, I don't know what these two or whatever the other tops. So I just select this one. So it selected it. But still you are in 3D mode. So you can select set plane view. Yeah. So it becomes 2D now. So you are now seeing the plane which you are sketching on now. Now you get here some options. Rectangle, line, point, but these are not the only options. You will see here a lot of options here. So circle, rectangle, everything is here for sketching, a lot of things. Or you can go to sketch and see all the options for sketching. For the descriptiveness, I will use the menu always, not the shortcut buttons, so that you don't have to struggle with the icons. So let's create a rectangle, because that's our first thing. So you create a rectangle. Now you get two options in here. You see? You can either give corners or center point and a corner. Like that, for different geometries, they have a lot of other options also. So I like this one, like this. So I select this. Then you can just click and do this. Click and click. Random, no worries. So this is, you see here, some relationships are already there. So if you zoom in here, you see a perpendicular side. Because Salome can be thought of as I told you, parametric, and it can have relationships with geometry. So in here, it says this line is perpendicular to this line. That's why this symbol is there. If you click on it and you can delete it also, then it's not anymore perpendicular. You can have a arbitrary shape there. Yeah. Now, what we need is basically we need to give the sizing. So for sizing, you will see here some sizing options. Or you can go to sketch again and say basically either horizontal distance or the length. You can click on it and click on a line and put the here. So it asks for the length. So no coordinates information because this is basically parametric modeling. You can do still with coordinates, I will show you later, but this is with just parametric modeling. So this is 8, so it becomes 8. So then this is 6, so I'll just put again click and put a 6 there. 6, so like this. You see, it's kind of rotated now. That's because the constraints are not enough to fully define what your geometry is. It's underdefined. You need more constraints. So another constraint you can put is basically, you can go to sketch and then say vertical and then say one of these lines. Or horizontal to the other one because it's perpendicular, it's there. If you over constrain, it will throw a warning in here saying it's over constrained. You can try. So if I put this one vertical and if I try to this one vertical, yeah, it's over constrained. It didn't apply. Yeah. It throws an error. Warning basically, not an error. If you over constrain your system. Let me double like this. Now still a problem. We don't know. Still this can be moved everywhere here. That's why it's still not constrained. You can just move it anywhere, but you cannot rotate it anymore. You cannot size it anymore. So to make it fully constrained, you can say this midpoint coincides with the origin. How do you do that? Go to sketch. There should be coincident. Yeah, this is a coincident. Click on it and click on the origin. So you see here first object, second object. So first object is origin. So it got it. Second object is basically the midpoint, or you can do an endpoint also. I don't care. Me, just do the midpoint. Didn't select. It didn't select actually. Yeah, it didn't do it. It didn't select. I think I didn't get it. A coincident. Yeah. It's the origin now. If it doesn't apply, that means you have a bound some conflicting constraint. Yeah, you see here, now it's fully green means it's already fully, in the your context, if you see it's fully green, that means it's fully constrained. It was red because I over constrained it somehow. Yeah. So I did not know what I put. I think I clicked on some other point and it got over constrained. So let's see. We can just make a new one. It's easy. Nope. Shaper. Sketch. And then this is a rectangle. Yeah. Okay. And then you need to do the distance. I think length. 8. 6. And that's it. So once you're finished with this, put always the tick. Otherwise, you might over constrain unknowingly clicking at some other point. That's what happened to me last time actually. I didn't press that tick. So it over constrained my system and then I cannot anymore have the coincident. Now it should be coincident should be fine. Yeah, now coincident worked. Nice. So tick, always tick. Don't forget. Like in GLE escape, this is tick. Clicking. Now I need the vertical one. So I think this is the vertical. Yeah, vertical constraint. Now you see it's fully constrained. Green means it's fine. That means you don't have any variables which are not defined for this geometry. So nice. It means greens fully constrained. So you can't move it anywhere like here. Now we need to create a circle. So that's the circle, or you can go to sketch and circle. You can select on the midpoint and then draw it like this. First draw no dimensions. Afterwards, you go again sketch and radius. There should be somewhere radius. Yeah, radius. Here. Radius. Click on the circle. And then, so the radius is basically, I think, 1.5. So it's fully constrained. So because we fixed it at the center point at the radius. So the circle is fully defined now. Okay, let's save. No, we cannot save. You need to go out save. If you want save now, click tick and then go get out of the sketch by green ticking it. So you go out of the sketch. Now you are not in the sketch mode. You cannot change the sketch anymore. Then you can save. I will save it in the, okay, this is super hard, basically with larger. Why doesn't it even show my? Okay, it only shows this folder for some reason. No idea. Okay, save. Yeah, okay, fine. Save. I saved it. Again, you can go back to sketch by right clicking. Okay, it's still saving. That's strange. Yeah, this is a log file, so I had a lot of redundant solvings. Basically, that's what it was warning about. Why it is? I think my computer is stuck because of this zooming thing. It cannot respond to zooming. It's stuck. Sorry. It came back to life. Yeah, it came back. Okay, you're back. So right click, you can go and edit sketch again. That's a nice thing. So you can always go back and change some things. So now you are in the sketch mode again. Anyways, we don't have to do anything in here because that's the geometry what we want. Now we want to create basically what do you call the shells. Okay, they should be in yeah, here. So you go out of the sketch mode and then go to build and click on shell. Then it will ask for faces for the shell because you need faces. So if you select, depending on what you select, you see here, it highlights differently. So you can select circle or this one. Yeah. So you see, it created a shell with a hole. Then press the tick. So shell is done. Again, save. Now shell is done. So you see, everything you do here, it appears nicely. So you can go back and change also. It's fine. Now you have the shell. Now the shapers part is done. Basically, shaper is just to shape your geometry. It can be 3D, 2D, whatever. Now we need to export this into a geometry because this is just shaper module. So how do you export? Where do I have it? It's yeah, in the features, export to geom. Click on it. So we export this shaper to geometry. Now you don't see anything happening, but fine. Now switch to geometry in here because these are the steps in meshing. And the model creation into geometry. Now you are in the geometry mode. So you see automatically the shell is there, which is came from the shaper. You can skip the shaper step if you like, fine. Then if you are in the geometry mode, you always need to work with XYZ coordinates. So if you want to create the same shape, I will show you how also after this example. So then you need to use like GID, XYZ coordinates, create the lines, create the surfaces, then like cut it out, like all of these things. That's the difference. It's up to you how you do it, basically. However you feel, yes. Yeah. So, okay, give me a second, this goes up. Can we just put it somewhere else? Because it's blocking the whole.
Maybe you can force it to hide by 5% all.
Height. Yeah, height. Yeah, nice. Thanks. It's fully hidden. Yeah, that's nice. Yeah, so what you have to do is go to shaper. Thanks for the hint. Yeah, go to shaper and then go to features and then export to geometry. Then it exports this shaper step to geometry so that geometries we can work on. You don't need the shaper step as I told you. You can fully start with the geometry. Then you are working with lines, edges, faces like that. Not with the parametric modeling, basically like with these relationships, it's hard. Yeah, so we go to geometry. Now you have the shell. Now we need basically some boundaries defined so that we can apply our boundary conditions as in GID. Same steps, nothing new. But how do you do that? You can say here right click on the shell, create group. Then you have to select which type. It's a node, line, surface, or volume. So in this case, first I will create the solid. So I will click on surface. Okay. Then you just give a name. So I will give the same name, solid. Yeah. There are multiple ways how you can get the areas. So what I usually do is I say select all, basically because it's only one surface. If you have multiple servers, select all, will select all of them, and then you can click on it to see which one is corresponding one. Then you can apply. Don't use apply and close because it will close, because we need to keep on applying boundary conditions, so we will only apply. Done. So you see here, solid is there. You see it's using shell something. The origin is from shell. Now we will create the left edge, which we had in GIE. So it's a line. So you switch to this one, the line one. And then again select all. Now you see a lot of lines are popping up because you have 5 lines. So you have 5, 1, 2, 3, 4, 5 numbers. Now you don't know which one is left edge. So you can click and then identify. Here you see, if you look at this edge now, if I click, so it disappears, right? That means 7 is this line. Then 9 is this line. You see, it disappears. The numbering might be different in your case, but yeah. And then 11 is bottom. 13 is, I don't know which one. 13 is a circle. Yeah, 13 is circle. So then 4 should be the left line. Like this. Yeah, this is one way. So I will show you the other way now. I will close of selecting. So you can go to here, shell. And there should be something called, okay, where is that? Yeah, explode. That's what I was looking for. So in the new entity, explode. What explode does is actually, it creates for every subtype a group name. The problem with this is actually, if you have really complicated geometry, it might create 30 different group names. Like I can do it. In here, you say shell, and then sub shape types, I need edges. I need to explode all the edges and have separate names for them. That's what I'm saying here. Then you say apply. You see 5 edges are coming. Now you can see also which edge is which one. So you select this. So you see some things disappear. Like this. So you can delete whatever you don't want. Now, that's another way. So there's no one way in Salome. There's a multiple ways to do the same thing. Even this same simple model. So let's see what we need. So we need this. So I will just rename this to be left edge. You can do it like that also. Left edge. And then this one is bottom. We don't need. So we delete it. Yeah. Then this one is circle, I think, right? Yeah, circle we don't need. We delete it. This one is, we need that. That's the load top. So we rename it to load. This is the right edge, so we rename it to right edge. Yeah. So this is the other way of doing it. Like that. So you save, fine. So now you have created the domains, basically. The next step is creating the mesh. Because now domains are identified, the boundary conditions are identified. Now we have to look at the mesh. So for that, what we do is we need to go to the next step, which is the mesh. Click on it. Yeah, you get something like blank in here. It's black. I don't think I can change the color of that. Yeah, it's by default black. Yeah, so you have nothing here. So first thing you have to do is select this shell one and go to mesh and create the mesh. Yeah. In here you get options. So since this is a 2D one, that's why 3D is disabled. And then you can give options for 2D, 1D separately because it's asking how do you want to mesh. So because Salome can do multiple meshes at the same time. And then you can combine them also afterwards. That's advanced meshing. You can just look at Google videos, YouTube videos for that. Because you can generate a mesh for 1D here and the 2D here separately and then combine them at a later point. Those kind of advanced stuff you can do in Salome. I'm not going for that. So we will do only 2D. In here, you have to select which type of mesh you want to have. So NetGen 1D, 2D free faces means actually triangular ones, unstructured ones. You can have structured ones also. Then as I told you, this one, you cannot really do structured. You need to break it down to some other component to do structure. This hold with plate, even though it's super simple, structure this you need to, it's more involved. So we will choose this one, NetGen 1D, 2D. Because we need to mesh 1D as well as 2D, we are saying in this same mesh. We are not going to do it separately. So that is easier for us. It's not a must always. Now, then you have hypothesis. That defines what are your mesh parameters. So you can click on this wheel here. You can say NetGen 2D parameters. Then you get this. So this is the overall size. As I told you here again also I am emphasizing these mesh sizes might not be adhered. It's just suggestion. If it can, it will follow. Otherwise, it will skip. So maximum size, I'm just going to put 0.2. Minimum size, I'm going to put 0.1. And fineness, moderate. You can just try different ones if you like this. And then press OK. So you see NetGen 2D parameters one of the default. Now we have custom parameters here. Now apply and close because we have the domain mesh now ready. Here you see mesh one like this. So I will save it again. So if you want to see the domain mesh, right click, compute. Yeah, you see domain mesh. So you see the summary, faces, edges, and everything. So you see the mesh now. Yeah, but there's a problem. So this will create a domain mesh, but it will not create subgroup meshes for the boundaries because for FEM, we have domain mesh for sure. We need that one. And we need to know the nodes of here and the connectivities of here, basically this line to apply the load. If you don't tell it to Salome, it will not create that by default. No. So how do you do that? You right click on this mesh one, say create a submesh. Yeah. Now the main mesh is mesh one. And then the geometry, it's asking for the submesh geometry. So you can select basically we need left edge from the geometry. Yeah, now it asks for the parameters. You can give separate parameters for that. So the type is wire. That's the basic one. It's because it's lines. It's only 1D. Here you see it's automatically 1D only. You select wire discretization. And then again it has a hypothesis. That means the parameters to define the wire. So you can click on this and say either you can do number of segments or local length. Up to you. It's just parameter. I just say local length. And I just say here 0.1 maybe. It's up to you. Yeah. Okay. So you see its local length. Yeah. So for the left edge. Apply. Now I'm not closing because I need to keep on doing it for multiple times. So I apply. So it should have created submeshes here, edge. Yeah, it created here submesh. Now I will apply the same for the right edge. So here you have to click on this if it is not activated. Then click on the right edge. It's selected. So I will use the same length. If you want to use a different length, you can again create a new local length. So then it will be a new local length in here. No, it will not override the other one. It will keep on creating these kind of hypotheses. as long as you want. So since I don't want it, so I will just use the same local length. Fine. Apply. Again, the same for the load, because we need that also for the boundary condition. I will use the same local length. Now I will just apply and close. So you can double check here. So load here, left edge, right edge, load. So you have this. You can rename these submeshes also to be perfectly nice. Yeah, but no one will read them. Actually, Kratos will not read them. Kratos only will read these names. Solid, left edge, load, right edge. Not the mesh names. Even though mesh names will be there in the final outcome of the Salome. Since you created now submeshes, okay, save it. You need to again recompute the mesh so that it will calculate the node and connectivities of the submesh. So you can right click, clear and compute. So it clears the existing one and computes the new mesh. Yeah, it should not change anything here. No, it will change because I give the sizing differently. Earlier I didn't give any sizing for the edges. Now I give sizing for the edges. So it will be for sure different. Now you see the edges are a little bit more refined because we gave specific sizing. And now we have separate groups for them also in the mesh. Nice. Yeah. So now the part of the Salome is done. So that we have now the mesh, groups, domains, everything which we need for Kratos. Now we just do is right click on the mesh and go to export and med. Med means mesh data file, basically it's short form for mesh data files. Med. And save it somewhere you can access. This like magnifying thing is killing my whole interface basically. Can't see anything. Okay, I will just do the desktop. Where's my desktop? I will create a Salome Sampos and Salome. Wait, give me a second, I will show you. So either you can do here mesh one, the main mesh, right click and export, or you can go here file export also. Both are same. Yeah. If you sorry, MED, yeah. That Kratos can read directly. That's why Salome and Kratos are coupled in a loose way. So MED is a like standard format, so Kratos can read it nicely. Yeah, now I just want to show you some things. Yes, stop. Yeah, so this file is fully binary, so you cannot open it unless you have HDF5 viewers. But it's HDF5 file. I don't know whether you know what is HDF5 file. It's a high definition file, I think HDF means. That means it can store a lot of big data really in a compressed manner. Tensors, matrices, high order tensors like fourth order tensors, no problem. So it uses the same format, even though it's MED. So if you change it to H5, then you can open it with, I don't know whether I have HDF view. Oh, I have. Oh. This is HDF5 viewer. Let's hope that it works. Because I didn't use it for a long time. Yeah. Okay, it doesn't work. Okay, fine. Anyways, it doesn't matter what is inside because it's not readable usually. It's hard to read what is inside, even though it's some text is there. Okay, fine. Now the Salome part is done. Let's close Salome. Okay. Yes. Okay. Yeah. Save. Sure. Yes. Now you have the mesh one med file. Where is my study file? I don't know where I saved it. Okay, fine. Yeah. As I told you, this is a geometry file. Now, how do we construct the main Kratos and the JSON files? Because those are the ones which are required. Geometry file, we now have a met. Instead of MDPA, earlier we had here MDPA file here. So you see MDPA, this is a mesh file, which has a node information human reader. Now we have it in a different format. It's called met. So geometry is done. Now we need to have the JSON and the main Kratos. How you can do it is actually, I would say, not the easiest. What you can do is you can go to Kratos Multiphysics. One way, not the only way. Go to examples and find the closest example you think which makes sense. Copy paste the JSON files, change them. That's what we always do. That's first one way. Another way is download the GID, the free version, create a really coarse mesh with whatever the boundaries you want. Like a really, like even though if it is a complicated component, create it with simple boundaries. We don't care actually with in the GID, you don't need to have to model the completed component as it is. It just need to represent the same boundaries only and create maybe 10 element case. Who cares? Because then generate the JSON files. You use those JSON files because you can use the free version forever. This is that or that. So since we created already the plate one, we can use it. That's why I did the first GID version here. So just copy this and then we will change it. So copy this, and this to the Salome one. This way. It will not work as it is because it doesn't know still we are reading a made file. Yeah. Now let's open VS Code in here so that we can change. I think it's opened. Yeah, desktop is open. Okay, fine. Okay, it again popped up. Hide. Okay, everything should be hidden. Yeah. First thing is, okay, close everything. Salome. So let's start with easy one. First thing is this materials because it's a simpler one file. So now we said model part name part. So this is coming from the GID. This submodel part. This name is coming from us structure. So this is coming from the GID, but we changed in our case it will be solid because we gave it a name solid. Not like in GID because in GID they put some prefixes. In Salome they don't. You can use the exact name which you have given. So this will be solid now. So the first change. And the structure is coming from here. So in here we say here the model part name is structure. So this is defined by Kratos. Submodel parts are automatically generated by the Salome now. So structure, that's why we put here dot. It says it's under structure dot solid. We have structure dot left edge, right edge also, and structure dot load also. So this we don't change anymore. Now we go here. Yeah, you can just change it to all of these also if you like, but I will keep it same because it doesn't matter for this one. In here it matters. Because now we are not reading MDPA. Because our input is made. It's a Salome input. MDPA is from the GIE. So you say here use input model part. Basically, you don't read. I will tell you how you read it in a separate line. So this is the change. How do you import the model part? Materials doesn't differ. This doesn't differ. Everything else remains same because we are solving the same case. That's why. Otherwise, you have to check those also. Okay. If you're that's why I'm telling you take the closest example or generate with GID with the closest having the same boundaries. Even though let's say that you have 5 boundaries in a complicated component, just create lines with 5 lines. So representing 5 boundaries. It doesn't matter where they are basically because JSON file is a text file. So then you can refer it in the med file the same names. Yeah. Then in here again we have to change because we don't have any more this one. We only have the left edge. So displacement constraint. Again, the right edge. Like this. And this is just the load. Yeah, just double check the others also whether they are valid. So this is valid. These two are still valid. Fine. Yeah. Now, since this is a little bit of complicated main Kratos, which was introduced recently, I will just show you a more simplified version which does the same. We can do it for this one first so that you know it works. So go to main Kratos. Basically, you delete everything. You don't need anything because it can be more simplified. This is for modularity, they made it like this. Delete everything. You don't need any of these. You will need Kratos Multiphysics. Then you can say def main. So you need a model that is the main container of the Kratos, basically. So you're now going a little bit of coding part as a starting point. So model is the main container of Kratos. So you can create a model by Kratos Multiphysics model. One pointer, when you say dot, the model doesn't pop up. It's because it's in C++ and we are working on it actually for Windows, how to make it there in the hinting. This is just for hinting. So the VS Code understands that there's a model. Only VS Code doesn't understand, it cannot create at the moment the C++ code. That's fine. So we are working on it. For Linux, it's fixed, but for Windows, not yet. So you get a model, and then you need to read the JSON file, which is the project parameter. So how do you read in Python? With open project parameters JSON. So use read only as file input. So you create parameters, which are Kratos parameters, which are Kratos multiphysics parameters. I'm typing them by memory because, okay, I'm living basically in Kratos. Yeah, I don't need the tooltips. But if you want to know what are the, like, even if your hinting is not working, what you can do is you can do this. Just say, let's say that your hinting is not working, but you need to know what are the available methods, like this one, because this is coming from me. You don't have to trust me. In any Python code, if you want to see, because there are some other libraries also, okay, some libraries also which this hinting doesn't work properly, you can do is print dir and the library name. It can be numpy, scipy, like this. And if you run it now, play with whole Python, you see all the available methods under that library. In Kratos, it's a lot of, because Kratos Multiphysics is a big library, so it has a lot of methods and everything. Yeah, you can see it like this. What are the available methods? This is a Python command, so it works in any Python for any library. Print dir Kratos Multiphysics. Right. So you will see somewhere in here parameters also. Here you see parameters are there. So that's what I was using, and then there should be a model also. Okay. Okay. There should be a model. Yeah, it's there. I don't know where. Yeah, the model is there. Fine. So here you need to give a string with parameters. So what we do is basically, so parameters, we say file input dot read. So it passes the whole file as a string to create a Kratos parameters. So this Kratos parameters is an interpreter for JSON. That's it. It has the same structure as JSON. It's just a Kratos class so that we can interface with JSON. That's it. It's nothing much. It's just JSON. Basically, you can think of this as JSON. Now what you need is you need to get the structural analysis. So how do you do that? From Kratos Multiphysics. This one you will have tooltips. Structural mechanics analysis. So analysis are the points where we can run something in Kratos always. There for every application there's separate analysis or many analysis. So for structural mechanics, there's this analysis. For fluid dynamics, you have a fluid dynamics analysis. For convection diffusion, you have a convection diffusion analysis. For optimization, you have optimization analysis. Like that, every application has its own analysis. So we can just say import the structural mechanics class. It's a class. Structural mechanics analysis. Now you can create a simulation which is of type of this analysis. You need here a model, which it says, and the parameters. Just pass it. You create a simulation. Then just say simulation.run. That's it. In here, you need to put the main. Like this. So we had really complicated code generated by GID for the modularity. we just simplified it because it's easier to follow us, to follow the course basically. So if you run it, it gives the same answer. Yeah. It gives the same answer. That complicated code is basically simplified. So it's simple as that. Yeah, now we do take this code for change it because I don't like to change the complicated code because this is a little bit complicated to understand. So we have this now. Let's change this to Salome. Now, if you run the Salome one, it will throw an error. Let's do that. Now, cd Salome, it will throw an error. Multiple errors, maybe. Yeah, it says here the solid is not found because we don't read the med file yet because we didn't give any information about the med file. So it throws that solid is not there. If you fix that, then there's some errors because still doesn't know where to find geometry because we didn't even copy the MDPA file here, only the med file. So we need to give that information. So how do you do that? You have to put some code in between. In the future, you might not be need to do that. You can do it in JSON, but at the moment, you need to do this. Basically, this part of the code, but it's good actually as a practice to get on board with the hands-on. So in here, what you can do is you need to create a med importer. How do you do that? Let's try first to show you the problems and then how to find out them also. For the med, this med format, we have separate video. It's in a separate application, import. You need to import that application. It's called med application. It doesn't pop up. Why? We haven't installed it. Go to your this same virtual environment. Then say Python -m pip install Kratos med application. That's the application which is interfaced with the med format in Salome. It's not in the core because Kratos should not know anything about any of these pipelines. That's how we keep it separate. Even for GID, it has a separate part. Yeah. So it installed med. Yeah. Unfortunately, there's a problem with the med in Python. In the pip one, if you have compiled, it's fine. You need to go to the Moodle page, which I sent you around. Because it will not work out of the box. Okay, let's show the error also. That's good for you to see. So now you see that med application pops up because I installed it in the environment as I just say Kratos med like this. Now let's try running it. Main Kratos. Yeah, you get this error. That's because the med library needs specific DLLs. At the moment, our Python repositories in the pip install doesn't allow uploading them, only for Windows. We are still working on it. We tried to fix it yesterday, but it didn't work. But for the course, we kind of have a workaround. So what you can do is go to the Moodle page to make it work. Go to onboarding. In there, there's a med application DLS. Download it. Don't worry, it will not harm your computer because those are legit libraries. So no worries about that. That's okay. Yeah, so if you go to downloads, I should have it somewhere here, medlibs. So I have a different name, but it's the same. Copy all of these files. And then paste it to, I will show you the location. Go to software, Python environment where you created. Kratos onboarding, lib, site packages. Go to Kratos Multiphysics, and there's the .libs folder. You will see some other libs, paste it there. Doesn't it work? Oh, okay. Let me again. Why didn't it copy? Did I? Yeah, copy it now. Yeah, just copy it there. That's it, basically. Now, if you run it, no errors unless the solid error, the early error. Yes. Sorry? Top imports. Yeah, sorry. Okay, again. Yeah. Structural mechanics analysis. So it should come under here when you say it should pop up. Did you fix this environment from the right bottom? Okay, maybe then just use the name structural mechanics analysis. So I don't know. It's a maybe VS Code version problem or not, because for some it pops up, some it doesn't. It's just VS Code. Yeah. The problem is our computers are so configured for VS Code, so we have forgotten actually like how we configured them also from the first place. But usually it should pop up. Yeah. This is one. Yeah, correct. Now you found it?
No, I'm trying to maybe get installed Kratos Multiphysics application.
Yeah, you need to install that first of all. Yeah, otherwise you don't get it. It's same for the med. You need to install. Separate it. You didn't have it, the structure. That's why. Yeah. Now you should have it because this is a Python, so it should be able to. But VS Code is should be able to do that. Yeah. Yeah. Now we have this. Now if you run it, you see no problems except for the problem with the solid problem, which med file doesn't read. Now let's read the med. If you like, you can do print dir Kratos med to see what is available in med. Since the Windows doesn't have the hinting yet, so you will see what is available in the med. Now you see. Okay. Let's put it in the here, not in the main. You see, the med has this med application, med model part IO, med testing utilities, rest is Python stuff. Only these four are Kratos related, rest is Python stuff. So we need the model part IO. That's what we need, input output, to read the med file. So we create that one here. So we say med model part IO equals Kratos med dot part IO. So you don't know the arguments. Yeah, you have to follow me basically. The first argument is basically the med file name. So what is that? Mesh1.med. Whatever the name you give. Then you just say read model part. Then you just say here, because you said in the parameters, if you look at, as I told you, you said you are working on the structure. So that's what you need to fill now with the med file. So you say here model dot get model part structure, and then fill it. What I'm saying in here is actually I don't need this line actually. So no, let's keep it so that it's easy to understand. Like this. First you create the IO. Then in the IO you have these methods. Read model part, write model part, everything is IO method. It's there. If you don't know actually what methods are available, you can again do this one out also. Print dir and put the object there. Here you see you have, oh no, we need to call this. It's called med model part IO. Sorry, my mistake. Called med model part IO. Yeah, you see, you have append, ignore, read conditions, read constraint, read elements, read model part, everything is there. So these are the methods available in here. Yeah. So we just use read model part. Don't need this anymore. So it should read it without any problems. Okay, where yeah, read. At least it suggests. Nice. Yeah, structure was not found. Okay, I need to put this one like a back in because it is the one who creates structure. Now you see it red. Med model part red, 1746 nodes, 208 geometries of line 2D, 3204 triangles, whatever. So you see that it's reading it somehow. But it's still geometries, remember, no physics information. Now we need to give all of this physics information. How do you do that? You need to create elements because Kratos geometries doesn't have physics, but elements has physics, like in normal frame elements. Yeah, for that, I would need to copy. I will just put it in there so that you can also copy. Because I also need to get it back. Yeah, so this is the, I will just show and explain it to you. Give me a second. So this is again some parameters like JSON. Basically, you need to pass to a Kratos modeler, which kind of generate from geometries elements. So in here, what we say is, this is the element list. The model part name is structure solid. So we know it has domain elements. And I want all of the geometries in the structure solid, which are triangle ones, to be of this physics type element. Small displacement 2D, 3A. How do you know these names? That I will cover in the afternoon session so that you can get all of these available names. Yeah, in the afternoon session, I will show you how to get all of these available names. And the conditions is boundary conditions. So it's load, and we use this one. This actually is taken from this guy. So you see here, same name. Same name. If you don't know, that's why I told you, you can use a simpler supercost measure in GID to get all of these names. Or use the closest example from the example repository. Yeah. So you have to do, this is the settings to do this. And then you need to have, this is the guy who basically changes it. It's from Kratos, so you just need to use it only. So I will just keep it for you, just you can copy paste. Like this. Yeah. So once you do this, if you run it, it should run without any troubles. Yeah, it still doesn't have any trouble. So it does whatever it does. It doesn't show anything like that. Yeah. This is there. Then what you need is basically you have created now physics. You need to put some properties into this physics, like the Young's modules and all those things. Because this will only create the elements, not assign any properties. So for that, you can just do iterate through every element and condition and put some properties. So how do you create in Kratos some dummy properties? It is called dummy properties. You can say model. It needs to be in the sub model part. Get model part. Structure. You can always do print dir to find out what is there. Create new properties. One is ID. It's just dummy ones which we put. We don't need to fill in because we already have the properties in structural materials. We need some dummy ones so that it has something, elements. Then you say for element in, okay, just do this here, basically structure equals this. And then you can take structure dot elements, so that you can iterate through every element of the structure, which is created by this here. So it will be small displacement 2d3 and once, and then you can say element dot properties equals dummy properties. So it's just dummy. So you can do the same for conditions. Conditions are boundary conditions, which are line conditions. Condition. Yeah, condition. So you have some dummy properties. So this should also run without a problem. Yeah, doesn't have any problems. It runs as far as I see. Now we have done everything. So we have read the made file and assigned some dummies. So now we can hand it over to the simulation, basically do the rest of it. So we just turn this on off. Let's hope that it runs. Okay, it throws an error. Ah, this one, it's good that I got this error to explain. Yeah. So what is this error? It's good that these errors are popping up. This error says the non-positive size. As you know, in FEM, so if you use triangles, it doesn't matter what is geometry of any type, you have this order of nodes. It should be in 2D, it should be anti-clockwise. Because we need to be efficient, we always assume in our size calculations, nodes are given in the anti-clockwise direction, so that sizes are positive. If it is in the clockwise one, then you get negative sizes. So that's what it's showing in here basically. To fix that, you need to go to basically Salome and invert the basically the node ordering. I will show you now how. First, I need to find this one. I think I saved it in here. Stop. No. Ah, yeah, study 2 finally found it. Yeah. Okay, open the study. And then you need to go to mesh. Here, the mesh mode, because that's where we have to change all the normals. If you like, you can just visualize the mesh, like again here. So you have the mesh. And then, wow, that's really large. I don't know why it is large. No idea. Yeah, see, this is the reorient phases. Or you should be able to find it in here also. Wait. Here. In the modification, reorient phases. Click on that. So it has dx0 here. So put dz to -1. So you reorient the phases basically. And apply and close. Yeah, 3200 first reverse. Now they reversed it. You just need to reverse it because there's only one way. See, the one direction or other direction. It doesn't matter you put -1 in that one or the other one basically because you just have to reverse it. That's it. Just needs to be reversed. Okay. Now you save and again export the mesh. I will save it the same location. Okay, good question is where? Desktop. Salome, let me show. So I will overwrite it. Overwrite. Fine. Now it's done. Now let's see. So we get the same error again. No, it works now. Nicely. It ran. Yeah. Now let's go and try to do the open source pipeline visualization. For that, we will use Paraview. That always happens. Give me a second. I always have to reinstall Paraview for some reason. It always crashes in Windows level. It doesn't take much time. I don't know why. I always reinstall Paraview in Windows. Yeah, it works now. So this is the para basically which I was talking about, the open source post processing one. So since I am magnifying, so it's super large. So you have a lot of filters here. So you see there are a lot of filters. Even actually you cannot see everything because yeah, to do everything. Okay, I guess I did again. Right, loading controls. Yeah. So now what you need is you need to open the file. So you can here open. Yeah, it looks for my network locations. Actually, that's why it's taking so much time. I do have it. Oh, I don't have. Yeah, I know why it is slow. I don't have this one. Yeah, yeah. Now. So it is looking at my network locations. Yeah. So now you go to desktop. You just say Salome plate with hole. So GAD output, parameter cannot read. So even only the VTK output. So you can do the same for the GAD output also. So it also writes the VTK output. Both should be the same basically. So you go Salome plate with hole, VTK output, you have the structure. And then you say apply. So you have the plate. And here you have the displacements. You will see a little bit more complicated list of variables when you do the final example of optimization. Because in there you will see a lot of variables here, which are for optimization, you have complicated stuff. For the simple stuff, no. You have the reactions and one with the stresses. So that's how you can visualize. Since this is a fine mesh, that's why you don't see the discretized values because we use the fine mesh and the GID. Otherwise, if you go in, so it should be discrete also at one point here. You'll see something like that. Yeah. So with this, I think, let me go to the presentation. Let to see basically. Yeah, I didn't miss anything. Yeah. Yeah, with this, we conclude the session for the morning. It's actually 15 minutes earlier, so that's nice. Any questions up to now about anything? Yeah. Okay, then we can meet at 1 o'clock after lunch. Yeah. The rest of the afternoon session fully will be nothing to do with Salome, GID, it's just pure Python. Basically, even the mesh will be generated by us manually in hand, basically, so it will take some time. So that we will show you every possible, I mean, all the function, most of the functionalities of Kratos, how do you do meshing, because you can do everything by hand also as a academic exercise. Yeah. So that's the target of afternoon, so that you know a little bit in detail how Kratos backend works, because this is just clicking and running, even though I did some magic commands in here. Basically, it feels like magic, I understand, but you will understand them in the afternoon. Okay. Yeah, see you at 1 o'clock then. Yeah. Thank you. I will stop the online version also, and then I will open it again at 1 o'clock. See you at 1 o'clock.